Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with EWRB. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we're learning Topic 11, Basic Electrical Theory, which is the foundation of nearly everything you'll do as an electrician. We'll go through how energy changes form, the meaning of Ohm's law, what resistivity is, how simple circuits operate, and how to calculate values in basic DC series and parallel circuits. We'll cover each part exactly as listed in the official guidelines. Let's get started. 11a Demonstrate how energy is converted through heat, chemical, magnetic and mechanical processes. Electrical energy can turn into different forms depending on the job the appliance is doing. Here are the four main ones you need to know. 1. Heat energy. When electricity flows through a resistance, it produces heat. This is how heaters, ovens, kettles, and toasters work. More current means more heat. 2. Chemical energy. Batteries use chemical reactions to store and release electrical energy. When charging a battery, electricity turns into chemical energy. When discharging, the chemical energy turns back into electricity. 3. Magnetic energy. Anytime current flows in a conductor, a magnetic field is created. This magnetic field is used in motors, transformers, solenoids, relays, and contactors. 4. Mechanical energy. Motors turn electrical energy into movement. This movement is used to drive pumps, fans, compressors, drills, and many industrial machines. Understanding energy conversion helps you recognize how different loads behave. 11b. Demonstrate knowledge of Ohm's law, material resistivity, resistor parameters, and introduction to measuring methods. B1. Ohm's law. Ohm's law shows the relationship between voltage, current, and resistance. Voltage equals current multiplied by resistance. Current equals voltage divided by resistance. Resistance equals voltage divided by current. We use Ohm's law all the time for troubleshooting, testing elements, and calculating current draw. B2. Power formulas. Power tells us how much energy a load is using. Power equals voltage times current. Power equals current squared times resistance. Power equals voltage squared divided by resistance. These formulas are essential for load calculations and for checking heating elements. B3. Resistivity. Resistivity explains why different conductors have different resistance. 1. Material type copper has low resistivity, so electricity flows easily. Steel has higher resistivity, so it has more resistance. 2. Length. The longer the conductor, the more resistance it has. 3. Cross-sectional area. A thicker conductor has lower resistance because there's more room for current to flow. 4. Temperature. Resistance increases as temperature rises. This is why hot cables have slightly higher resistance. 4. Resistor parameters. These are the main things you need to know when identifying or selecting resistors. 1. Resistance value. This tells you how much the resistor limits current. 2. Power rating. This tells you how much heat the resistor can safely handle. If the resistor receives more power than its rating, it can burn out. 3. Tolerance. This tells you how close the actual resistance is to the printed value. For example, a 100 ohm resistor with 5% tolerance can be between 95 and 105 ohms. 4. Temperature coefficient. This tells you how much the resistance changes as temperature changes. All of these help you choose a resistor that is safe and accurate. B5. Measuring methods. Electricians use several instruments to measure electrical values. Here's what each one does, explained in simple spoken style. Multimeter used to measure voltage, current and resistance. Clamp meter used to measure current flow without disconnecting any wires. Insulation resistance tester, MEGA, used to check the quality of insulation on cables and appliances. Fault loop impedance tester used to check the earth fault path and confirm that protective devices will trip quickly. RCD tester used to check trip times and leakage current sensitivity of RCDs. Choosing the correct tester keeps the work safe and makes your results accurate. 11C. Demonstrate knowledge of how electrical energy is produced from various forms of energy. Electricity is produced using electromagnetic induction. This means a voltage is generated when a conductor moves through a magnetic field. In New Zealand, most electricity comes from hydro turbines, geothermal steam, wind turbines, gas or steam turbines. All of these spin a generator, and the generator produces electrical energy. This is how our 50 Hz supply is created. 11D. Explain the operation of a simple practical circuit including current path, circuit control, load, EMF source and conductors. A simple circuit needs a few basic parts to work properly. 1. The supply source. This could be a battery, a transformer, or the 200 and 400 volt main supply. 2. The phase conductor. This carries current from the supply to the load. 3. The neutral conductor. This brings the current back to the supply to complete the circuit. 4. The load. This is any device that uses electrical energy, heaters, lamps, motors, outlets, and so on. 5. The protective earthing conductor. This provides a safe path for fault current so protective devices can trip. 6. The control device. Switches and isolators control when the load is powered. Understanding how these parts work together helps with polarity testing, RCD operation, reading wiring diagrams, and troubleshooting faults. 11E. Determine the resistance, voltage and power in any part of a DC series and/or parallel circuit using practical knowledge and safe use of measuring instruments. These circuits help you understand the basic behavior of voltage, current and resistance. In a series circuit, the same current flows through every component. The voltages add together. The resistances add together. If one part fails, the whole circuit stops working. This type of circuit is common for things like old-style Christmas lights or simple indicator circuits. In a parallel circuit, the voltage is the same across every branch. The currents divide depending on the resistance of each branch. The total resistance is always less than any of the individual resistances. If one branch fails, the other branches may keep working. Parallel circuits are used in homes for lighting and socket outlets. Basic DC calculations. Using Ohm's law and the power formulas, you can calculate current, voltage, resistance, power. These calculations appear often in electrician theory exams, especially in heating element questions and basic circuit analysis. Bringing it all together. To bring everything together, Topic 11 gives us the core understanding of how electricity behaves. We looked at how energy changes form, how voltage, current, and resistance relate, how conductor properties affect resistance, how simple circuits work, and how to calculate values in DC circuits. These fundamentals are used everywhere, in testing, fault finding, cable selection, protection, and almost every part of the electrician's job. Once you understand Topic 11, the rest of electrical theory becomes much easier to follow. Summary. Electricity converts into heat, chemical, magnetic and mechanical energy. Ohm's law, V equals I times R, I equals V divided by R equals V divided by I. Resistivity depends on material, length, area, and temperature. Resistor parameters, value, power rating, tolerance, temperature coefficient. Measuring methods include multimeters, clamp meters, insulation testers, RCD testers. A simple circuit needs EMF source, conductors, load, and switching. Series, currents equal, resistances add, voltages divide. Parallel, voltage equal, current divides, total resistance decreases. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whit Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we're learning topic 12, Systems of Supply, which explains how electricity is generated, transmitted, distributed, and supplied to consumers in New Zealand. We'll also look at star and delta connections, load balancing, three-phase power calculations, neutral currents, and then move into the multiple earth neutral (MEN) system, which is the foundation of electrical safety in low-voltage installations. We'll go clause by clause, exactly in the same format as topics 11. Let's begin. 12.1 New Zealand Electrical Supply System. 12.1a. Illustrate with labeled diagrams the New Zealand electrical supply system showing the generation, transmission and distribution systems. New Zealand's supply system starts at generation, where electricity is produced using hydro, geothermal, wind, and gas/steam turbine stations. The generators produce electricity at around 11 to 18 kilovolts. This is stepped up to high transmission voltages, typically 110 kilovolts or 220 kilovolts, for long-distance transmission across the country. Closer to towns and cities, substations step the voltage down to 33 kilovolts for sub-transmission and then to 11 kilovolts for local distribution. Finally, pole-mounted or ground-mounted transformers reduce the voltage to 400 volts three-phase or 230 volts single-phase for customer use. This process ensures efficient delivery of power over long distances and safe supply to consumers. 12.1b. State the typical voltages involved in each of the above areas. Typical New Zealand supply voltages include 11 to 18 kilovolts at generation, 110 kilovolts and 220 kilovolts for transmission, 33 kilovolts for sub-transmission, 11 kilovolts for local distribution, 400 V three-phase and 230 V single-phase for final consumer supply. These values are important to remember for both practical work and exam questions. Now let's look at the main characteristics of a series circuit. 12.1c. Draw and label the New Zealand three-phase four-wire distribution systems supplying three-phase consumer, two-phase consumer, single-phase consumer. New Zealand uses a three-phase four-wire system consisting of three-phase conductors and one neutral. A three-phase consumer receives all three phases and the neutral, giving them 400-volt phase-to-phase and 230-volt phase-to-neutral connections. A two-phase consumer uses any two phases, giving them a 400-volt supply between phases. A single-phase consumer uses one phase and the neutral, giving them a 230-volt supply. This flexible system allows a wide range of loads to be supplied easily. 12.1d. State the relationship between line/phase voltage and currents for star/delta. In a star connection, the phase voltage is 230 volts and the line voltage is 400 volts. The line current is the same as the phase current. In a delta connection, the phase voltage equals the line voltage, but the line current is the phase current multiplied by the square root of 3. These relationships are essential for understanding three-phase load behavior and for performing transformer and motor calculations. 12.1e. State the advantages of balancing the load over the three phases. Balancing the load across all three phases reduces neutral current, minimizes voltage drop, improves efficiency, reduces heating of supply equipment, and provides more stable voltage for consumers. A well-balanced system is safer and more reliable, and it reduces stress on the transformer and distribution network. 12.1f. Calculate power in a three-phase load. Three-phase power is calculated using the formula. Power equals the square root of 3, multiplied by the line voltage, multiplied by the line current, multiplied by the power factor. This formula is used in cable sizing, motor load calculations, and protection selection. Electricians must be confident using it because it appears frequently in exams and real-world work. 12.1g. Determine neutral current in a three-phase star-connected load. In a balanced star-connected system, the neutral current is zero because the three-phase currents cancel each other out. In an unbalanced load, the neutral carries the vector sum of the phase currents. The more unbalanced the phases are, the higher the neutral current becomes. Excessive neutral current can cause overheating and voltage imbalance, so understanding unbalance is essential for safe design and operation. 12.2 Multiple Earth Neutral, MEN, System 12.2a. Explain how the MEN system is configured. The MEN system connects the neutral conductor to the installation's earth bar using a solid MEN link. The neutral is also earthed at the distribution transformer. The earth bar is connected to an earth electrode. This creates multiple connection points between the neutral and true earth. The system ensures the neutral stays close to earth potential and provides a low resistance path for fault current, allowing protective devices to disconnect quickly. 12.2b. Explain reasons for earthing neutral conductors at multiple points in the LV distribution system. Earthing the neutral at multiple points stabilizes the neutral voltage, reduces touch voltages, ensures high fault current for rapid disconnection, and increases safety across the entire network. Without multiple earthing, the system would be less stable and fault clearance less reliable. 12.2c. List the features of the MEN system. Key MEN features include: the neutral is earthed at the transformer and the main switchboard. The MEN link joins the neutral and earth bars. The earth electrode connects the installation to real earth. Protective earthing and bonding connect to the earth bar. The fault path is low resistance to ensure fast disconnection. These features work together to enhance safety and ensure correct operation of protection devices. 12.2d. Explain the implications of the MEN link being missing. A missing MEN link is extremely dangerous. Without the MEN link, exposed metal parts may rise to full phase voltage during a fault. Earth fault loop impedance becomes high. Fault current may be too low to operate protective devices, meaning the installation remains live and unsafe. The installation becomes a serious shock hazard. A missing MEN link must be treated as a critical fault. 12.2e. Explain that downstream distribution type systems may be connected to a MEN installation provided the same essential features are maintained. Downstream systems, such as generators or isolated supply sections, can be connected to a MEN installation as long as they maintain the same protective earthing principles. There must only be one MEN link, the earthing must be correct, and the fault path must allow protective devices to disconnect quickly. As long as these conditions are met, downstream systems remain safe and compliant. Bringing it all together. To bring everything together, Topic 12 teaches us how electricity is generated and delivered across New Zealand, how the three-phase four-wire system works, why load balancing matters, and how to calculate three-phase power and neutral currents. It also explains the MEN system, which is the foundation of electrical safety in low-voltage installations. Once you understand the supply system and MEN principles, the rest of electrical protection theory becomes much easier. Summary. New Zealand supplies start from 11 to 18 kV generation, then step up to 110 or 220 kV for transmission, and step down to 33 kV and 11 kV for distribution. Our three-phase, four-wire system gives 400 volts between phases and 230 volts from phase to neutral. In a star system, the line voltage is √3 times the phase voltage, and the currents are the same. In a delta system, the line voltage is the same as the phase voltage, but the line current is √3 times the phase current. For three-phase power, we use the formula √3 times voltage, times current, times power factor. Balanced loads help keep the neutral current low and reduce voltage imbalance. The MEN system joins the neutral to earth at the switchboard and at the transformer. If the MEN link is missing, it creates a major shock risk because the installation loses its reference to earth. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whit Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Welcome back. Today we are learning Topic 13, Electrical Protection, which is one of the biggest and most important topics in the electrician theory syllabus. This topic is all about keeping people, equipment, and property safe from electrical faults. We'll look at what excess current is, why it's dangerous, the different types of protection devices, and a long list of terms every electrician must understand. Then we'll cover residual current devices, RCDs, in detail, including types, classifications, requirements and AS/NZS 3000, maximum trip currents from the ESRs, and testing methods. Finally, we'll move on to isolating transformers, their principles, their safe use, and why they are rated in kVAR rather than kW. There is a lot to cover here, so I'll take it slowly and clearly. Let's begin. 13.1 Protection. 13.1 is state what is meant by the terms rated current and excess current protection. Rated current is the maximum continuous current a device or cable can safely carry without overheating or being damaged. Excess current protection means using devices like fuses or circuit breakers to stop the current from rising above that safe level. When too much current flows, the device disconnects the supply to prevent overheating, fire, or equipment failure. 13.1b describe the danger of excess current to cables and equipment. Excess current heats up cables and equipment. If the current is too high, the insulation softens, melts, or carbonizes. Once insulation breaks down, metal parts can become live, starting fires or causing shocks. Equipment can burn out or fail internally. Excess current is one of the biggest causes of electrical fires, which is why correct protection is essential. 13.1c state forms of excess current protection, close excess current protection, coarse excess current protection. There are two forms of excess current protection, close and coarse. Close excess current protection is the more sensitive type. It will operate within 4 hours when the current reaches 1.5 times the designed load current of the circuit. This means the protective device responds sooner when the current is above normal levels. Close protection is found in modern protective devices such as MCBs and HRC fuses. Coarse excess current protection is less sensitive. It will not operate within 4 hours at 1.5 times the designed load current. This protection operates much later under moderate overcurrent levels and is mainly associated with older devices such as rewirable fuses. Rewirable fuses were common in older homes, but AS/NZS 3000 does not allow rewirable fuses to be installed in new installations in New Zealand. They may remain in older systems but cannot be used for new work. So the difference is simple. Close protection equals operates within 4 hours at 1.5 times design current. Coarse protection equals does not operate within 4 hours at 1.5 times design current. That is the full distinction between the two of excess current protection. 13.1d explain the following terms applicable to sub-circuit protection: voltage rating, current rating, utilization categories, breaking capacity and kVAR rating. Voltage rating is the highest voltage a protective device can safely withstand without flashover. Current rating is the maximum current it can carry continuously without overheating. Utilization categories describe how the device behaves with different loads, for example, general loads or motor loads. Breaking capacity, or car rating, is the maximum fault current the device can safely interrupt. The kVAR rating links to the supply fault level and tells us how much energy the device must withstand. 13.1e describe the construction, operation and applications of semi-enclosed rewirable fuses, HRC fuses, miniature circuit breakers, cartridge fuses, fusible links, magnetic overload relays, thermal overload relays. A semi-enclosed rewirable fuse uses fuse wire that melts under overcurrent, simple but coarse protection. HRC fuses are sealed with a calibrated element and sand filler, giving fast and safe interruption at very high fault currents. MCBs use thermal and magnetic mechanisms to trip on overloads and short circuits and can be reset. Cartridge fuses are sealed one-time fuses used in appliances or control gear. Fusible links melt at high temperatures and protect heating appliances. Magnetic overload relays use a solenoid that trips instantly on heavy overloads, often with time delay. Thermal overload relays use a bimetal strip that bends as it heats, tripping the circuit at sustained overloads. 13.1F Understand and explain the following terms. Current rating, voltage rating, fusing current, utilization category, tripping factor, cutoff characteristic, time versus current characteristic, category of duty, discrimination, backup protection, rupturing capacity, prospective short circuit, current sensitivity, earth fault loop impedance. Current rating is the safe continuous current the device can carry. Voltage rating is the highest safe operating voltage. Fusing current is the minimum current needed to melt a fuse. Utilization categories describe application types, such as general or motor loads. Tripping factor is how much current above the rating will trip an MCB. Cutoff characteristic shows how fast a device stops rising fault current. Time current characteristic shows trip time at different fault currents. Category of duty describes voltage and braking capacity combinations. Discrimination means only the nearest protective device trips during a fault. Backup protection uses a higher rated device upstream to handle large fault currents. Rupturing capacity is the maximum fault current the device can safely break. Prospective short circuit current is the highest fault current available at a point. Sensitivity is the imbalance current level that makes an RCD trip. For example, a 30 mA RCD often trips earlier, around 18 to 22 mA. So sensitivity tells you how small the leakage current needs to be before the RCD disconnects. Earth fault loop impedance is the total resistance of the fault path when an active conductor touches an earthed part. Low loop impedance means high fault current and fast tripping. High loop impedance means slow or no tripping, which is unsafe. 3.2 Residual current devices, RCDs. 13.2 Understand that RCDs provide supplementary protection to users of electrical equipment. RCDs provide supplementary protection, which means they add an extra level of safety on top of fuses and MCBs. Fuses and MCBs only protect against overload and short-circuit currents. They do not trip when small leakage currents flow through a person. An RCD protects people by detecting very small leakage currents, usually 10 mA or 30 mA, that could pass through the human body. If any current leaks to earth, for example, through a person touching a faulty appliance, the RCD senses the imbalance and disconnects the power within milliseconds. This fast disconnection greatly reduces the chance of electric shock, muscle freeze, can't let go, burns, or ventricular fibrillation. So in simple terms, RCDs are designed to protect people, not equipment, and they do this by disconnecting the supply very quickly when even a small leakage current occurs. 13.2b Demonstrate knowledge of the maximum tripping current and operating times for RCDs to be deemed electrically unsafe. Regulation 24 Regulation 24 tells us when an RCD is considered electrically unsafe. These rules apply to both fixed RCDs in installations and portable RCDs used with appliances. For a standard 30 mA RCD used for electric shock protection, it is unsafe if it fails any of the following. 1. It must trip within the required time at its rated current. It must disconnect all live conductors within 300 milliseconds at 30 mA. If it takes longer than 300 milliseconds, the RCD does not provide safe protection. 2. It must trip very quickly at 5 times its rated current at 150 mA. It must trip within 40 milliseconds. If it does not meet the 40 milliseconds requirement, it is unsafe. 3. It must not trip too early at low leakage current. The RCD must allow at least half of its rated residual current before tripping. So for a 30 mA RCD, it must not trip at 15 mA or below. If it trips too early, it fails Regulation 24. 4. It must meet AS/NZS 3190 performance requirements. If the RCD does not match the testing limits in AS/NZS 3190, it is electrically unsafe. 5. Additional rules for 10 mA RCDs. For RCDs protecting children, as /NZS 3000 mandatory situations, and medical patient locations, rated current must not exceed 10 mA. Must trip within 40 milliseconds at rated current. Must trip within 40 milliseconds at 5 times rated current, 50 mA. Must not trip below 45% of rated current. So in simple terms, to be safe, an RCD must trip fast enough at the right leakage current, must not trip too early, and must meet the exact time current limits in Regulation 24. If it fails any of these tests, it is legally unsafe and must be replaced. 13.2c explain the checking and testing requirements to ensure that RCDs installed for protection against shock are Type A for New Zealand. In New Zealand, all RCDs used for personal protection must be Type A. Type A RCDs detect AC leakage and pulsating DC leakage, which is important because many modern appliances, such as induction cooktops, EV chargers, speed controllers, and switch mode power supplies, produce DC components that a Type AC RCD may not detect. When checking RCDs, we confirmed 3 things. 1. Correct type. The device must be clearly marked Type A or better. If the marking is unclear or missing, the RCD cannot be used for shock protection. 2. Correct installation. It must be wired correctly, supply connected to the right terminals, and all active conductors passed through the sensing coil. 3. Correct performance. Using an RCD tester testing a 30 mA RCD. A. Test at half times rated current, 15 mA, no trip. B. Test at rated current, 30 mA, must trip within 300 milliseconds. C. Test at 5 times rated current, 150 mA, trip within 40 milliseconds. D. Test at both 0 degrees and 180 degrees phase angles. If the RCD fails any test, it is electrically unsafe under Regulation 24 and must be replaced. 13.2d Understand the operating principles of an RCD. An RCD works by comparing the current in the active conductor with the current returning in the neutral. In a healthy circuit, these currents are equal. The RCD contains a toroidal core and a sensing coil. If some current leaks to earth, through a person, a metal frame, or damaged insulation, the active and neutral currents become unequal. This imbalance produces a small magnetic signal in the sensing coil. The RCD detects this instantly and trips the internal switch mechanism, disconnecting all live conductors. RCDs do not protect against overload or short-circuit faults. That is the job of MCBs and fuses. The RCD's purpose is purely shock protection, reducing touch voltage duration. 13.2e Be aware of how RCDs are classified. RCDs can be classified in several ways. Method of operation. Some RCDs work independently of supply voltage, electronic-free designs, while others require line voltage to power their sensing circuit. Type of operation. Types include AC, A, F, and B. Type A is required for NZ shock protection because it detects pulsating DC. Type B detects full DC and is used for EV chargers and specialized equipment. Number of poles and current paths. RCDs can be 2-pole, single-phase, or 4-pole, 3-phase. They must disconnect all live conductors, including neutral. Adjustable residual operating current. Some industrial RCDs allow the operating current to be adjusted, for example from 30 mA to 300 mA. Resistance to unwanted tripping from voltage surges. Better quality RCDs include filters to reduce nuisance tripping caused by lightning or switching surges. Behavior and presence of DC components. Type AC RCDs may be blinded by DC, so NZ requires Type A or better. Protection against external influence. RCDs must have suitable IP ratings and be mounted where physical damage or moisture is controlled. Method of mounting. DIN rail, socket outlet RCDs, SRCDs, portable RCDs, PRCDs, or fixed RCBOs. Method of connection. Some require hard wiring, others plug-in, or appliance integral types. 13.2f Understand the operational characteristics of RCD types and how different available RCDs operate, including RCCB, residual current circuit breaker, provides residual current protection only, no overload protection. RCBO, residual current breaker with overcurrent protection, combines RCD and MCB functions in a single device. This is the most common residential option. SRCD, socket residual current device, a socket outlet with built-in RCD protection. Often used where an RCD cannot be added to the switchboard. PRCD, portable RCD, used on construction sites, workshops, or with handheld tools. Protects the user even when the fixed installation lacks RCDs. Voltage-independent RCDs operate even when supply voltage is lost. Required for Type A shock protection in many situations. Voltage-dependent RCDs need supply voltage to power their internal electronics. Used mostly in PRCDs. Typical residual current ratings 10 mA for high-risk areas, 30 mA for personal protection, 100 mA or 300 mA for fire protection. Classification relating to DC components. Type A responds to AC and pulsating DC, required in NZ. Type F and Type B handle more complex waveforms. Load leakage currents. All appliances leak a small amount of current. Circuits with many appliances may approach the RCD's trip threshold. This affects RCD selection and circuit grouping. 13.2G methodologies for installing RCDs in residential, industrial, and commercial situations, single-phase and three-phase. Residential installations, as/NZS 3000 requires 30 mA RCDs on all final subcircuits, including lighting and socket outlets. RCBOs are now preferred because they avoid losing all lighting when one circuit trips. Commercial installations often require discrimination, ensuring only the closest RCD trips. This may involve using selective S-type RCDs, delayed RCDs, or splitting loads across circuits. Industrial installations, more complex loads, such as motors, drives, and three-phase equipment, may require RCDs with higher surge immunity, adjustable sensitivity, or Type B detection for DC components. Three-phase circuits must use 4-pole RCDs that disconnect all live conductors, including neutral. 13.2H Understand and apply the principles relating to protection for safety in as/NZS 3000 and the role RCDs play in protection for additional safety in damp situations. As/NZS 3000 requires RCDs wherever people are likely to be exposed to shock hazards. Damp situations, such as bathrooms, laundries, pools, outdoor areas, washdown areas, or any place where water reduces body resistance, require RCD protection because the human body resistance is lower when wet. Faults become more dangerous. Leakage current flows more easily. RCDs help ensure automatic disconnection of supply before shock becomes dangerous. 13.2I Understand and apply the requirements of as/NZS 3000 regarding RCD installation and the use of RCDs with handheld electrical appliances. As/NZS 3000 requires 30 mA RCDs for almost all final subcircuits in homes. Handheld appliances in commercial and industrial workplaces must be RCD protected because the risk of shock increases when tools are held in the hand or used in damp or conductive environments. Tools such as grinders, drills, saws, and site equipment must be powered through RCD protected circuits or PRCDs. 13.2J Understand considerations of installing 10 mA RCDs for protecting areas of increased risk in children. 10 mA RCDs provide very sensitive protection. They are used in locations where even small leakage currents are dangerous, such as early childhood centers, schools, medical treatment areas, disabled care facilities, equipment used by or near children. As/NZS 3000 recommends 10 mA RCDs where children may directly contact equipment or where additional shock protection is required. 13.2K Testing RCDs to ensure compliance with Regulation 24. Testing includes 1. Visual check. Confirm it is type A or better and correctly installed. 2. Test button. Confirms the mechanical action only, not enough for compliance. 3. Full RCD tester verification. O must not trip at half times rated current. O must trip within 300 milliseconds at rated current, 30 mA. O must trip within 40 milliseconds at 5 times rated current, 150 mA. O must trip at both 0 degrees and 180 degrees test angles. If any requirement fails, the RCD is electrically unsafe and must be replaced. 13.3 Isolating transformers. 13.3 describe the basic operating principle of an isolating transformer. An isolating transformer has a primary winding and a secondary winding, with no electrical connection between them. The only link is the magnetic field in the transformer core. Because the secondary winding floats, meaning it is not connected to earth, touching one conductor on the secondary does not complete a circuit back through the human body. This dramatically reduces the risk of electric shock. So in simple terms, an isolating transformer separates the output supply from earth and reduces shock risk by preventing fault current from flowing through a person. 13.3b Explain why an isolating transformer provides maximum safety when used with only one electrical appliance connected. An isolating transformer gives the highest level of protection when supplying only one appliance. Here's why. When only one device is connected, the secondary side is still fully isolated from earth. If a person touches one live conductor, their body does not complete a circuit, so only a tiny, harmless current flows. There is no return path for sustained fault current to flow. But if more than one appliance is connected, a person could touch two different metal parts at different voltages, which recreates a shock path. So for maximum safety, use an isolating transformer with one appliance only. 13.3c Explain why it is necessary, when two or more electrical appliances are connected simultaneously to one isolating transformer, their earth continuity conductors are bonded together at the transformer but must not be earthed. If more than one appliance is connected to an isolating transformer, all exposed metal parts must be kept at the same electrical potential. To achieve this, the earth continuity conductors must be bonded together at the transformer. This ensures all appliance frames sit at the same voltage. That way, if a person touches two appliances, there is no voltage difference across their body. However, this bonding must not be connected to the installation earth. If it were earthed, the isolation effect would be cancelled, and shock risk returns. So the rule is simple. Bond the earths together, but do not connect them to the actual earth. 13.3d Understand that the isolating transformer may be used in conjunction with other approved safeguards for extra protection where considered desirable. In some situations, isolating transformers are not used alone. They can be combined with other protective devices to improve safety, such as RCD protection, double insulated tools, reduced voltage systems, extra physical insulation or barriers, medical-grade isolation systems. This is common in medical treatment areas, laboratories, workshops, or specialist equipment where the risk is higher. So the key message is: isolating transformers can add another layer of electrical protection when combined with other safeguards. 13.3e Explain why transformers are rated in kVA and not watts or kW. Transformers are rated in kVA, which stands for kilovolt amps, not kW. Here's why. Transformers carry voltage and current, but they do not control power factor. Power factor depends on the load, not the transformer. The transformer must be able to handle full voltage and current, regardless of whether the load is resistive, inductive, or capacitive. kVA includes the total current times voltage without considering power factor. kW only measures useful power, not the total load on the transformer windings. So the simple spoken reason: transformers are rated in kVA because they must carry the total current and voltage, no matter what the power factor is. Bringing it all together. To bring everything together, Topic 13 has shown us how important electrical protection is for keeping people, equipment, and property safe. In 13.1, we learned why excess current is dangerous and how protective devices prevent fires, equipment damage, and cable overheating. We looked at the difference between close and coarse excess current protection, and we learned a large set of key protection terms such as breaking capacity, discrimination, fusing current, and earth fault loop impedance. We also covered how fuses, MCBs, HRC fuses, cartridge fuses, and overload relays work, and why each type is used for different faults or equipment. In 13.2, we studied RCDs in depth. We looked at how RCDs operate, how they detect leakage current, and why NZ requires Type A RCDs for personal protection. We covered classification, installation methods, and the behavior of RCDs in different applications. We also learned the Regulation 24 performance limits, which tell us when an RCD is electrically unsafe, including the exact trip currents and operating times. We looked at where RCDs must be installed, how they protect people in damp situations, and when 10 mA RCDs are needed for children and high-risk environments. In 13.3, we covered isolating transformers, how they reduce shock risk by separating the supply from earth, and why they offer maximum protection when supplying a single appliance. We looked at bonding requirements when more than one appliance is used and learned that the protective earths must be bonded together but not earthed. Finally, we explained why transformers are rated in kVAR instead of kW. Topic 13 brings together all the fundamental ideas behind electrical protection and builds the foundation for safe electrical practice. Understanding these principles is essential for real-world installations and for passing the electrician theory exam. Summary: excess current overheats cables and equipment and must be controlled. Close protection trips early and protects against overloads. Coarse protection trips only on large fault currents such as short circuits. Key protection terms include breaking capacity, fusing current, discrimination, tripping factor, utilization category, PSC, sensitivity, and earth fault loop impedance. Fuses, HRC fuses, MCBs, cartridge fuses, and overload relays each protect against different types of faults. RCDs detect leakage current and protect people from electric shock. Type A RCDs are required in NZ because they detect AC and pulsating DC leakage. Regulation 24 sets exact trip currents and times for 10 mA, 30 mA, 100 mA, and 300 mA RCDs. RCDs are used widely in residential, commercial, and industrial installations. 10 mA RCDs are used for children, patient areas, and high-risk situations. Isolating transformers reduce shock risk by separating the output from earth. When multiple appliances are supplied, earths must be bonded together but not earthed. Transformers are rated in kVAR because they carry voltage and current independently of power factor. Welcome to this EWRB Electrician Theory Exam training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam teaching guidelines. Welcome back. Today we are learning topic 14, electrical safety, personal, which is one of the most important topics for every electrician. This topic focuses on how electricity affects the human body, how to isolate equipment safely, the legal responsibilities under the Health and Safety at Work Act and the electricity safety regulations and the safe work practices we must follow every day. We'll begin with the effects of electric shock, what happens to the body, why current level matters, and why contact conditions change the level of risk. Then we'll look at proper isolation and tagging procedures, including lock-off, written procedures, and the prove-test-prove method. After that, we'll cover legislative responsibilities for employers and workers. Finally, we'll move into a large section on safe working practices, including PPE, hazardous environments, high voltage risk, fire procedures, and rescue methods. Let's get started. 14.1 Effects of current. 14.1 Demonstrate knowledge of the physiological effects of electricity on humans. Electric shock occurs when current flows through the body along a path, for example, hand to hand or hand to foot. The severity depends on current level, time in contact, the person's skin condition, and whether the body is wet. Electricity can cause muscle contraction and can't let go, breathing difficulties, burns, internal and external, nerve damage, heart rhythm problems, including ventricular fibrillation, which is often fatal, unconsciousness or death. Even small currents can kill under the right conditions. The longer the contact, the worse the injury. 14.1b Explain why peak voltages, contact types, and victim conditions affect the severity of electric shock. Peak voltage stresses insulation more than RMS voltage, so the higher the peak value, the greater the chance of insulation failure and shock. Touching active and neutral, or active and earth, completes a dangerous circuit through the body. Conditions like wet hands, sweat, cuts, or punctured skin reduce body resistance. Lower resistance means higher current, which increases the severity of shock. Longer contact time allows more current to flow, making injuries more serious. 14.2 Isolation procedures. 14.2 State the benefits of working on equipment that has been isolated. Isolation removes the risk of electric shock and prevents a circuit from being energized while work is happening. It creates a safe environment, limits unexpected movement of machinery, and ensures everyone on site knows the equipment cannot be switched on. 14.2b Explain the safety tag system. A safety tag is a warning device placed at an isolator. It identifies who isolated the equipment, when, and why. It warns others not to operate the equipment. A tag alone does not prevent operation, it must be combined with lock-off whenever possible. 14.2c State the benefits of using the safety tag system. Tags improve communication on site, reduce accidental energization, and help maintain compliance with workplace procedures. They ensure everyone knows equipment is isolated and being worked on. 14.2d Explain methods used to isolate and lock off equipment. Locking off means physically securing an isolator in the off position using a lock or device so it cannot be operated. A personal lock and tag must be applied, and only the person who installed the lock may remove it. Lock-off prevents accidental or unauthorized re-energization. 14.2e Explain the importance of the prove, test, prove rule. This rule ensures the test instrument is working and that the circuit is actually dead. 1. Prove the tester on a known live source. 2. Test the circuit to confirm it is dead. 3. Prove the tester again. It prevents false zero readings caused by damaged meters, flat batteries, or wrong settings. 14.2f Explain conditions covering the use of safety tags, and correct placement and removal. Tags must be placed at the isolation point, filled out correctly, and used together with personal locks where practicable. Removal must follow workplace procedures. Usually only the person who applied the tag may remove it, unless authorized by a supervisor. 14.2g Detail written isolation procedures. Written isolation procedures describe identifying all energy sources, isolating and locking off, applying tags, testing dead, carrying out the work, removing locks, and restoring power safely. These procedures support legal compliance and ensure consistent safe practice. 14.3 Legislative requirements for workplace safety. 14.3 Employer responsibilities under legislation. Under the Health and Safety at Work Act 2015, the employer, PCBU, must provide safe equipment, tools, and PPE, train workers and provide supervision, manage hazards and risks, maintain equipment in safe condition, provide emergency procedures. Employers must ensure electrical work is carried out safely and to standards like AS/NZS 4836 and the Electricity Safety Regulations. 14.3b Employer responsibilities under legislation. Employees must take reasonable care of their own safety, not put others at risk, follow procedures and instructions, Use supplied PPE, report hazards or unsafe conditions. Competent workers must follow training and site rules. 14.4 Safe Working Practices. 14.4 Explain the importance of identifying hazards to ensure safety of workers, public and property. Electricians must constantly look for hazards and act to eliminate, isolate, or minimize risks. This protects themselves, other workers, the public, equipment, and property. Hazard management is the foundation of safe electrical practice. 14.4 We need to be conversant with electricity safety regulations. Electricians must understand ESR requirements to ensure all work is safe and compliant. Knowing the regulations supports correct installation, testing, and certification. 14.4 See importance of correct tools, clothing, and equipment. Tools must be fit for purpose, in good condition, and used correctly. Clothing such as ARC-rated protective gear must match the job. Any specialized equipment requires proper training. 14.4 The importance of preliminary safety checks. Before starting work, assess the site. Identify hazards. Check ladders, scaffolding, and height equipment. Ensure tools and PPE are suitable. This prevents accidents before work begins. 14.4 Good housekeeping promotes safety. A tidy work area prevents slips, trips, and falls. It also reduces fire hazards and creates a culture of professionalism and safety. 14.4 Personal protective equipment, PPE. PPE includes gloves, mats, eye protection, safety harnesses, and insulated tools. PPE must be to an approved standard, kept in good condition, and replaced when worn. 14.4 Regular checks of safety equipment. Tools and PPE must be checked regularly for damage and correct operation. Faulty equipment must be repaired or removed from service immediately. 14.4 Why insulated tools are necessary. Insulated tools protect against accidental contact with live parts by stopping current traveling through the tool into the user. They must be rated for electrical work. 14.4 Outdoor and damp situations. Moisture lowers body resistance and increases shock risk. When outdoors or in damp environments, electrical appliances must be supplied from an isolating transformer or protected by a Type A RCD. 14.4 Dangers when working with metal ladders and tools. Metal conducts electricity and increases shock risk. Use fiberglass ladders and avoid metal tools near live equipment. 14.4 Dangers working in explosive atmospheres. Any spark can ignite flammable gases or vapors. Equipment must be de-energized and confirmed isolated before removing covers. Only use X-rated gear where required. 14.4 Procedures when a fire is discovered. Raise the alarm, evacuate, and call emergency services. Use a fire extinguisher only if trained and only to escape or stop a small fire. 14.4 Rescue of a person in contact with live equipment. Do not touch the victim unless the power is isolated. Switch off the supply, use a dry non-conductive object if needed, and provide first aid/CPR once safe. 14.4 Fire extinguishers suitable for electrical fires. For electrical fires, use only dry powder or CO2 extinguishers, both Class E. Never use water or foam on live electrical fires, because they can conduct electricity and make the shock risk much higher. 14.4 Dangers when working on high-voltage fittings. HV work includes risks such as arcing, burns, step and touch potentials, and inadequate clearance distances. Only trained and authorized personnel may work near HV. 14.4 Precautions for circuits with capacitors or stored energy. Capacitors can stay charged even after the power is switched off, so we must treat them as live until proven safe. As/NZS 3000 says any capacitor over half a microfarad must discharge to below 50 V within 1 minute if rated up to 650 V. 5 minutes if rated above 650 V. Before working on the circuit. 1. Isolate and lock off the supply. 2. Prove test prove your tester. 3. Test the capacitor terminals to make sure the voltage is below 50 V. 4. If still charged, use the correct discharge method, never short it with a tool. 5. Follow the warning label. Ensure capacitors are completely discharged before working. So in short, isolate, wait the required time, test for 0 volts, and only work once the capacitor is safely discharged. 14.4 Q need for a second competent person. A second competent person is required when risk is high or live testing is needed. They assist in emergencies and ensure procedures are followed. 14.4 Dangers of short circuits. Short circuits create extremely high fault currents, causing arc flash, fire, and explosive force. Proper protection and PPE are essential. 14.4 S concepts associated with high voltage equipment. Risks include induced voltages, step and touch potentials, creepage distances, unstable potentials. Work must follow HV safety standards and safe approach distances. 14.4 T Electrical arcing hazards. Arc flash can cause arc eye, severe burns, blast pressure, and molten metal. Wearing arc-rated PPE and using correct procedures is essential. 14.4 ULIV HV work not permitted without written approval. Electricians cannot work on live high voltage lines or equipment without written approval from the asset owner. 14.4 V explain that under Schedule 1-2 electricians are permitted to operate works, electrical installations, switching of works, etc., if competent and approved by the asset owner. Under Schedule 1-2 of the Electricity, Safety, Regulations, some tasks are not classed as prescribed electrical work. These include operating works, operating electrical installations and switching. This means an electrician can carry out switching or operate equipment as long as they are trained, competent, and have the asset owner's approval. So in short, if the task is listed in Schedule 1-2, an electrician can do it, but only when competent and approved to do so. Connecting everything together. To bring everything together, Topic 14 teaches us how electricity affects the body, why correct isolation is essential, and how legislation supports safe work. We covered safe tagging, lock-off, PPE, and the prove test prove method. We also explored safe work practices for ladders, fire, high voltage areas, explosive atmospheres, stored energy, and rescue procedures. Understanding these safety principles is critical for staying alive, protecting others, and meeting your legal responsibilities as an electrician. Summary. Electric shock effects depend on current, duration, voltage, and body condition. Isolation and tagging prevent accidental energization. Prove test prove is essential before touch. Employers and workers have responsibilities under the HSW Act and ESRs. PPE must be suitable, inspected, and maintained. Use insulated tools and fiberglass ladders for electrical work. Damp or outdoor locations require RCDs or isolating transformers. Stored energy, capacitors, and HV equipment require special precautions. Use only CO2 or dry powder extinguishers on electrical fires. Never work on live HV equipment without written approval. Safe work practices protect workers, the public, and property. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whit Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we're learning Topic 15, Transformers and their applications. Transformers are one of the most important components in electrical systems. They appear in power stations, distribution networks, workshops, switchboards, control circuits, and many everyday appliances. In this lesson, we'll go through the entire topic in detail, beginning with the principles of transformer action, calculations, construction, losses, regulation, tap changes, and winding configurations. Then we'll look at voltage transformers, VTs, also known as potential transformers, followed by current transformers, CTs, which are essential for measurement and protection. Let's go through each clause one by one, just as written in the guidelines. 15.1 General. 15.1a. Explain the principles of operation for the double wound transformer and the auto transformer. A double wound transformer has two separate windings, a primary and a secondary, wrapped around an iron core. When AC flows in the primary, it creates a changing magnetic field. This magnetic field induces a voltage into the secondary. There is no electrical connection between the two windings, only magnetic coupling, and this provides electrical isolation. An auto transformer works differently. It uses a single winding, with tapping points to create different voltage levels. Part of the winding is shared between primary and secondary. Auto transformers are smaller, cheaper, and more efficient, but they do not provide isolation, so they must be used carefully where isolation is required for safety. 15.1b. State the formulae and perform transformer calculations involving voltage ratios, current ratios, turns ratios and kVAR ratings. Transformer calculations are based on simple ratios. The turns ratio equals the voltage ratio, and the current ratio is the opposite. So, N1 over N2 equals V1 over V2, and equals I2 over I1. Voltage ratio matches the turns ratio. Current ratio is the inverse of the turns ratio. And the power rating in kVAR is voltage times current, divided by 1000. If the secondary has more turns than the primary, it steps voltage up. If it has fewer turns, it steps voltage down. Because transformers are very efficient, power on the primary side is roughly equal to power on the secondary side. A higher voltage on one side means lower current on that side and vice versa. These formulas appear frequently in electrician theory exams, so we must be confident using them. 15.1c. Describe the basic construction of a power transformer. A power transformer consists of a laminated iron core, primary and secondary windings, insulation between the windings, oil or air for cooling, and an external tank with bushings for connections. The laminated core reduces eddy current losses, and the windings are wound onto the limbs of the core. Larger transformers use oil for cooling and insulation, and the oil circulates through radiators or pumps to remove heat. 15.1d. Explain why the low-voltage windings are generally placed closest to the core and why special additional insulation separates them from the high-voltage winding. The low-voltage winding is placed closest to the core because it carries higher current and needs better mechanical support. Placing it close to the core minimizes leakage flux and improves efficiency. The high-voltage winding is placed further out and separated by additional insulation. This prevents arcing and ensures safe spacing from the core and LV winding. Extra insulation protects against high voltages that could break down at the inner layers. 15.1e. Explain the terms iron losses and copper losses and the practical methods of reducing these losses. Iron losses occur in the core and include hysteresis losses from magnetizing the iron and eddy current losses caused by circulating currents in the laminations. These are reduced by using high-grade silicon steel and thin, insulated laminations. Copper losses occur in the windings from I2A heating. These are reduced by using thicker conductors, copper of low resistivity, and ensuring the transformer operates within its rated current. Reducing losses improves efficiency and reduces heating. 15.1f. Explain that the kVAR rating of a transformer is limited by the temperature of the core and windings. A transformer's kVAR rating is limited by how hot the core and windings can safely become. If the transformer carries too much load, heating increases and insulation can break down. Overheating reduces life expectancy and may cause internal faults. The rated kVAR ensures the transformer operates within safe temperature limits. This is why cooling systems, oil, radiators, fans are important. 15.1g. Describe the methods employed to dissipate the heat energy from the cores and windings of various transformer types. Small transformers rely on natural air cooling. Larger ones use oil that circulates around the windings and through radiators. Some systems use forced air fans or oil pumps for additional cooling. Very large transformers may use oil-to-water heat exchangers. Proper cooling prevents overheating and protects insulation. 15.1h Describe the effect of the load current on the secondary terminal voltage of a transformer. As load current increases, voltage at the secondary terminals tends to drop. This drop is caused by internal resistance of the windings and leakage reactance. Under heavy load, the voltage may sag noticeably. Under light load, voltage is close to the rated value. Understanding this behavior helps electricians identify voltage regulation issues. 15.1 I explain the term regulation as applied to transformers. Regulation is the percentage change in secondary voltage between no load and full load conditions. A transformer with good regulation maintains stable output voltage even as load varies. Poor regulation means voltage drops significantly under load. Lower regulation percentage is better. 15.1j Explain that the regulation of a transformer can be maintained by incorporating tap changing. Tap changes adjust the number of turns on the winding, allowing the output voltage to be corrected when load conditions change. On load, tap changes adjust taps while the transformer is energized. Off-load tap changes must be adjusted when the transformer is de-energized. Tap changing helps maintain stable voltage for consumers. 15.1k Explain how the primary and secondary windings of a three-phase transformer are configured to achieve these four basic combinations. Star-star, star-delta, delta-star, delta-delta. In a star-star connection, both primary and secondary are in star, giving phase to neutral voltages and allowing a neutral connection. In a star-delta transformer, the primary is star and secondary delta, often used for certain industrial loads. In a delta-star transformer, the primary is delta and the secondary provides a neutral point, common for distribution networks. In a delta-delta configuration, both windings are delta, useful where no neutral is required. Each connection changes line and phase voltage relationships and is chosen based on the application. 15.2 Voltage transformers, VTs, PTs. 15.2 Describe a voltage transformer, its operation and applications. A voltage transformer, VT, steps high system voltages down to safe levels for metering, protection relays, and instrumentation. It operates like a normal transformer but is designed for accuracy and safety. VTs are used in substations and switchboards to measure high voltages indirectly. 15.2b State the common secondary voltages of a voltage transformer when supplied at its full primary voltage. Common secondary voltages of VTs are 110V, 63.5V, or 100V, depending on the metering system. These lower voltages allow meters and protective relays to operate safely without exposure to high voltages. 15.2c Using typical symbols, show how voltage transformers would be represented on diagrams. On diagrams, VTs are shown using a standard transformer symbol with one side connected to high voltage and labeled appropriately. Although we are not drawing diagrams here, electricians must recognize VT symbols on schematic diagrams for metering and protection circuits. 15.3 Current transformers, CTs. 15.3 Describe the current transformer, its operation and applications. A current transformer, CT, steps down high current to a small, measurable current, typically 5A or 1A. CTs allow safe current measurement and feed protection relays and switchboards. They work by wrapping the primary conductor through a core and having many turns on the secondary. They are used in metering, protection, and large industrial installations. 15.3b Explain the term burden as it relates to current transformers. The burden is the total load connected to the CT secondary, including meters and wiring resistance. CTs are designed to operate accurately within a certain burden. If the burden is too high, the CT may saturate or give inaccurate readings. Understanding burden ensures reliable metering and protection. 15.3c state the common secondary current ratings of current transformers. Common CT secondary ratings are 5A and 1A. These standard values allow relays and meters to be designed safely and consistently across the industry. 15.3d using typical symbols, show how CTs would be represented on diagrams. CTs are represented on diagrams using a standard symbol showing a primary conductor passing through a core with secondary windings. While we are not drawing here, recognizing CT symbols is essential for reading protection and metering diagrams. 15.3e state the precaution that must be taken before disconnecting the load from a current transformer. Before disconnecting the load, the CT secondary must be short-circuited. An open-circuited CT secondary is extremely dangerous. It can generate very high voltages because current has nowhere to flow. This can damage instruments, arc to nearby metal, or injure workers. So the rule is, never leave a CT secondary open. Always short it before disconnecting the meter or relay. Bringing everything together. To bring everything together, topic 15 shows us how transformers work, how voltage and current ratios relate to turns ratio, how losses occur, and why cooling is essential. We learned how different winding configurations affect supply, how tap changes maintain voltage, and how VTs and CTs are used for measurement and protection. Understanding these principles is essential for reading switchboard diagrams, selecting equipment, and performing safe installation and testing in real electrical systems. Summary. Transformers operate using electromagnetic induction. Turns ratio determines voltage and current ratios. LV windings are close to the core for mechanical strength and efficiency. Losses include copper loss, iron loss, eddy currents, and stray losses. Cooling may use air, oil, radiators, pumps, or fans. Voltage regulation drops under load, tap changes correct it. Three-phase connections include star-star, star-delta, delta-star, delta-delta. VTs provide accurate low-voltage signals from high-voltage systems. CTs step down current for metering and protection. CT secondary must be short-circuited before disconnection. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whit Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we're learning topic 16, Selection of Cables, one of the most important topics for safe and compliant electrical work. Choosing the correct cable isn't just about picking a size from a table, it's a full design process. You must consider current, voltage rating, temperature, installation method, maximum demand, earth fault loop impedance, voltage drop, and short-circuit performance. When you understand how all these factors fit together, sizing a cable becomes a logical and structured process. Let's go through each subtopic step by step. 16a. Explain that the cable selection process involves factors such as the current and voltage rating, environmental conditions, length of run, earthing requirements, mechanical factors and additional considerations including derating factors and prospective short-circuit currents. When selecting a cable, we must consider several essential factors. The current rating tells us the minimum current the cable must carry continuously without overheating. The voltage rating must match or exceed the supply so the insulation is not overstressed. Environmental conditions such as ambient temperature, thermal insulation, and how the cable is installed affect how much heat it can safely dissipate. Hotter environments reduce cable capacity, so derating factors must be applied. The length of the run affects voltage drop. The longer the cable, the greater the voltage lost along its length. The cable must also support the earthing requirements, ensuring the earth fault loop impedance is low enough for protective devices to disconnect quickly. Mechanical factors such as whether the cable is buried, exposed, or subject to impact or abrasion also determine the cable construction. Finally, the cable must withstand prospective short-circuit currents, ensuring it can survive the initial energy until the protective device operates. 16b. Provide examples and explain how a cable is chosen for a stated application considering all of the above factors. When choosing a cable for any application, the same structured process must be followed. You start by identifying the design load and determining the installation conditions. This allows you to select the correct installation table for the cable type and method. Then you consider all derating factors, temperature, grouping, and insulation, and apply them to the cable's current carrying capacity. You ensure that after derating, the cable can still carry the required load. Next, you assess voltage drop to ensure it is within allowable limits for the supply. You also verify that the cable supports the required disconnection time by checking the earth fault loop impedance. Short circuit performance must be checked to confirm the cable can tolerate the energy of a fault until the protective device clears it. Only when all these elements meet the requirements can the cable be considered suitable. 16c. Determine cable type and size required for a sub-circuit under specified load conditions, using the appropriate parts of AS/NZS 3000 and AS/NZS 3008.1.2 for a stated application. To determine the correct cable type and size for a sub-circuit, you start with the design load and select a cable type appropriate for the installation, such as TPS, conduit wire, XLPE, or flexible cable. You then choose the appropriate installation method, which determines the current carrying capacity table you use. From there, you apply any environmental derating factors that reduce cable performance. Voltage drop must be checked to ensure the sub-circuit receives adequate supply. Earth fault loop impedance must be verified to ensure disconnection occurs within the required time. Finally, the cable's short-circuit capability must be checked against the prospective fault current. When all requirements are satisfied, the cable size is acceptable. 16d. Determine the maximum demand for domestic and non-domestic mains and submains in accordance with AS/NZS 3000 to 2007. To determine maximum demand, diversity rules must be applied. Maximum demand is not simply the total of all connected loads, instead, it is the load realistically expected to operate at the same time. Different types of loads have different diversity allowances, and these are set out in AS/NZS 3000. You apply the appropriate rules for lighting, socket outlets, appliances, and heating or cooling equipment to establish the installation's realistic peak loading. That value then becomes the basis for selecting mains, submains, main switches, protective devices, and distribution equipment. 16e. Determine the cable type and size of mains and submains for given applications. When we select mains and submains, the stakes are higher. These cables carry much larger currents, they often run long distances, and they form the backbone of the whole installation. Because they supply multiple sub-circuits, any mistake in cable selection can affect the entire building. The first step is choosing the correct cable type for the environment. Flexible cables such as PVC, TPS, or rubber sheath types are typically used only where movement or flexibility is required. Fixed wiring includes TPS, conduit wire, XLPE cables, neutral screened cables, and steel wire armored cables. Underground cables are usually XLPE or neutral screened types because they provide greater mechanical strength and moisture resistance. Aerial cables include aerial bundled conductor and figure 8 types, which are designed to withstand UV exposure, wind movement, and outdoor mechanical stresses. After selecting the cable family, you then assess all the conditions that influence cable performance. You consider the conductor material, normally copper or aluminium, because each has different current carrying characteristics. You check the maximum conductor temperature allowed by the insulation, because hotter cables can carry less current. Ambient conditions such as air temperature and soil temperature must be taken into account. These determine whether derating or re-rating applies. You then evaluate the level of mechanical protection required. Mains and submains are often exposed to greater physical risks, so armored or screened cables may be needed. Next, you identify the installation method, whether the cable is enclosed, buried, clipped, in conduit, or aerial. Each method has a different current carrying capacity and may require different correction factors. You must know the maximum demand of the installation, because this defines the minimum current the cable must support. The length of run must be considered because longer cables create more voltage drop. If several cables are grouped together, grouping factors reduce allowable current carrying capacity. The chosen cable must have adequate current carrying capacity after all derating factors have been applied. It must also withstand the short circuit energy, meaning it survives the fault current long enough for the protective device to disconnect. Finally, the cable must meet the requirements for voltage drop and earth fault loop impedance, ensuring that supplied equipment operates correctly and protective devices trip within the required time. Only when all of these conditions are satisfied can a cable be accepted for use as a main or sub-main. 16F. Demonstrate sound understanding of installation techniques for a wide range of low-voltage cable types in accordance with AS/NZS 3000 and AS/NZS 3000 in 8.1.2. Different installation methods change how a cable behaves thermally and mechanically. Cables in conduit lose heat slowly, so their current carrying capacity is reduced. Cables on trays or clipped in free air cool more effectively and can carry more current. Underground cables require consideration of soil conditions and may need additional mechanical protection. Aerial cables require insulation that withstands sunlight, temperature swings, and mechanical movement. In every installation method, you must consider the conductor temperature rating, the effect of ambient conditions, and grouping with other cables. These factors determine whether the cable must be derated. Voltage drop and earth fault loop impedance must always remain within the required limits, regardless of installation method. 16G. Candidates are expected to demonstrate a good appreciation for selecting the correct and appropriate protective device associated with the cable chosen for the stated application. The protective device must be chosen to match the cable's ability to carry current safely. The protective device rating cannot exceed the cable's current carrying capacity after all derating has been applied. The protective device must also disconnect quickly enough to prevent damage during faults. This means checking the disconnection time, the breaker curve, the earth fault loop impedance, and ensuring the device has sufficient short circuit rating. Once the device is correctly matched to the cable, the circuit can be considered properly protected. Bringing it all together. To bring everything together, cable selection is a systematic design process. We identify the load, choose the correct installation method, apply all derating factors, and confirm voltage drop, loop impedance, and short circuit performance. For mains and submains, we also calculate maximum demand. Every step ensures the cable remains safe under normal operation and during fault conditions. When you follow this process consistently, choosing the correct cable becomes straightforward and fully compliant with the standards. Summary. Cable selection must consider load, voltage rating, temperature, installation, and environment. Derating factors reduce current carrying capacity and must be applied. Voltage drop and earth fault loop impedance must stay within limits. Maximum demand determines mains and submains. Short circuit capacity must exceed prospective fault currents. Installation method greatly affects cable capacity. Protective device rating must never exceed cable current carrying capacity after derating. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we're moving into topic 17, switchboards and isolation devices. This topic is all about understanding how electrical installations are controlled, protected, and safely isolated. Switchboards are the central point where electricity is distributed, and isolation devices allow us to safely work on circuits without risk of electric shock. We'll start by defining what main switchboards, distribution boards, and switchgear are. Then we'll look at the special requirements for different types of switchboards, especially main and min switchboards. After that, we'll go through the AS/NZS 3000 requirements for the location, access, fire protection, environmental conditions, metering, and short-circuit ratings of switchboards. We'll also cover the main earthing requirements, which are critical for safety and correct fault protection operation. Finally, we'll look at the different isolation devices used on switchboards and how they ensure safe disconnection of circuits. By the end of this topic, you'll understand not only the terminology, but also the safety principles and compliance requirements behind modern switchboard design and operation. 17a. Define the terms main switchboard, and switchgear. When we talk about switchboards and isolation devices, S/NZS 3000 gives us very clear definitions, and it's important to understand them exactly as the standard intends. A switchboard is an assembly of protective devices and switching equipment. It may contain switchgear, meters, instruments, busbars, and all the connecting wiring. The purpose of a switchboard is to distribute electricity safely to submains or final subcircuits, or in many cases, both. In simple terms, it's the organized panel where all the breakers, fuses, and protection equipment are arranged. A main switchboard is the particular switchboard that controls the supply to the entire installation. This is the board where the incoming supply arrives from the electricity network. It contains the main switch that allows the whole installation to be isolated. Because it is the primary control point, it must meet stricter installation and safety requirements. Switchgear refers to the equipment used to control, switch, protect, or isolate electrical energy. This includes circuit breakers, fuses, isolators, load break switches, contactors, and any other devices used for switching or protection. These devices allow circuits to be turned on or off safely and to disconnect faults quickly enough to prevent damage or danger. So, the switchboard is the panel, the main switchboard is the first and most important one in the installation, and the switchgear is the equipment inside that does the actual switching and protection. 17b. Special requirements for main switchboards, MEN switchboards, and distribution switchboards. When we talk about main switchboards, MEN switchboards, and distribution switchboards, each of them has specific requirements under S/NZS 3000. A main switchboard must safely receive the incoming supply and provide the main point of isolation for the entire installation. It must have the main switch clearly labeled, proper barriers to prevent access to live parts, and enough space for safe operation and maintenance. Ventilation, clearances, blocking arrangements, and correct fault ratings are all essential because this board carries the highest fault levels in the whole installation. A MEN switchboard has extra responsibilities because it includes the main earthing connection and the main earth neutral link. This means the neutral bar, earth bar, bonding connections, and MEN link must all be installed exactly as required by the standard. The physical connection must be secure, identifiable, and accessible for inspection. Because the MEN link plays a key role in the protection system, the switchboard must maintain low earth fault loop impedance and provide reliable bonding to all required parts. A distribution switchboard, sometimes called a subboard, is supplied from the main board and distributes power to circuits in a specific part of the installation. It must have correctly rated protective devices, proper segregation, clear labeling, and safe access. Even though fault current is lower than at the main board, the board must still meet the required short-circuit ratings, enclosure requirements, and wiring space. Across all boards, S/NZS 3000 requires safe access, correct IP ratings, mechanical strength, suitable ventilation, and proper marking so that electricians can operate and maintain them safely. 17c. Requirements for switchboards, location, access, fire protection, environment, metering, fault levels. When designing or installing a switchboard, S/NZS 3000 sets out a list of requirements that help ensure safety and reliability. First, the location must allow the switchboard to be installed securely, kept dry, and protected from hazards. It cannot be placed in dangerous or obstructed areas, and the environment must be suitable for electrical equipment. Next, the board must allow safe access to the wiring and switchgear. Electricians must be able to operate switches, replace fuses, reset breakers, and carry out testing without risk. Access must not be blocked, cramped, or hazardous. Switchboards must provide protection against the spread of fire, which means using enclosures and materials that limit fire propagation. Wiring inside the board must be arranged so that faults cannot easily cause fire. Some installations require fire-resistant barriers or separation between switchboard compartments. The environment and mechanical conditions must be considered. This includes the level of dust, moisture, heat, chemicals, vibration, and potential mechanical impact. The board must have an enclosure rating suitable for the conditions, such as indoor, outdoor, wet areas, or corrosive environments. Switchboards must also allow for revenue metering requirements. The energy distributor may require space for meters, ceiling points, access for reading, and compliance with their installation standards. Finally, switchboards must be designed and rated for the prospective short-circuit current levels at their point of installation. The switchboard frame, bus bars, and all installed switchgear must withstand the maximum fault current long enough for the protective device to operate. This ensures the board won't be damaged or fail dangerously during a fault. 17D Application of AS/NZS 3000 and earthing requirements for MEN switchboards. At MEN switchboards, AS/NZS 3000 requires very specific earthing arrangements to make sure the protection system works correctly. The MEN system relies on a single, correctly installed main earthing conductor, a main earth bar, and a main earth neutral link. This link is the connection point between the neutral bar and the earth bar, and it must be located only at the MEN switchboard unless the installation is designed otherwise under special conditions. All protective earthing conductors, bonding conductors, and connections to the electrode system must return to this point. The integrity of these connections is essential because earth fault loop impedance depends on a low resistance path through the MEN link. Poor connections increase the fault impedance and may prevent protective devices from tripping within the required time. The switchboard must keep the earthing system accessible for inspection, secure against mechanical damage, and protected from corrosion. AS/NZS 3000 also requires proper identification of the MEN link and bars, correct sizing of earthing conductors, and reliable bonding to all exposed conductive parts. Overall, the MEN switchboard is the heart of the earthing system, and the standard ensures the installation remains safe and compliant. 17E Isolation devices used on switchboards. Switchboards use a range of fittings and accessories as isolation devices, and AS/NZS 3000 requires that these devices allow safe disconnection of electrical circuits. The most common isolation devices include main switches, load break switches, circuit breakers used as isolators, fused isolators, lockable isolators, and disconnect links. These devices must be able to fully open all active conductors of a circuit to prevent electric shock or accidental energization. Each device must be clearly labeled, easily accessible, and mechanically capable of being operated safely. The handle or operating mechanism must give a clear on and off indication. Some devices must be lockable in the off position to allow safe maintenance. In addition, devices must comply with switchgear standards and have adequate current and fault ratings for the circuits they control. All isolation devices must be installed so that workers can safely disconnect power before working on equipment, making them a critical part of electrical safety and safe work procedures. Bringing it all together. Now that we've covered the topic, let's bring everything together. Switchboards form the backbone of an electrical installation. They gather the incoming supply, distribute it safely to different circuits, and provide controlled access to switchgear and protective devices. Understanding the terms main switchboard, and switchgear ensures we can correctly identify the roles and responsibilities of each part. We saw that main and MEN switchboards have tighter requirements because they carry the highest fault levels and because the MEN link forms a critical part of the earthing system. We also went through the AS/NZS 3000 requirements for switchboard location, access, fire protection, environmental suitability, metering arrangements, and fault level considerations. These requirements keep the installation safe for the public, operators, and electricians. Finally, we looked at the isolation devices found on switchboards. These devices ensure that circuits can be completely disconnected so electrical work can be carried out safely and confidently. Overall, Topic 17 builds the foundation for understanding safe switchboard design, installation, and operation. Summary. A main switchboard receives the incoming supply and provides the main isolation point. A switchboard distributes power and houses protective devices and switchgear. Switchgear includes all devices used to switch, control, and protect circuits. Main and min switchboards must meet strict AS/NZS 3000 requirements for safety, enclosure, labeling, and earthing. Min switchboards must contain the main earth-neutral link and all required bonding connections. Switchboards must have safe access, proper location, fire-resistant construction, correct IP rating, and adequate ventilation. Revenue metering requirements must be met where required by the distributor. Switchboards and switchgear must be rated for the prospective short-circuit current at their installation point. Isolation devices must disconnect all active conductors and be clearly labeled, accessible, and safe to operate. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we are learning Topic 18, Basic Electronics and Semiconductor Devices. This topic is all about understanding how common electronic components work, what they do in real circuits, and how they behave under different electrical conditions. We will go through each semiconductor device, how it functions, how it reacts to temperature, and how it can be damaged if not handled correctly. We'll also look at transient voltages, PIV ratings, rectifiers, transistors, SCRs, triacs, and how filters smooth DC outputs. By the end of this lesson, you should clearly understand how these devices work and why they are important in both small electronic circuits and electrical trade applications. Topic 18a. Explain the function, characteristics and typical applications of the following devices: diodes, SCRs, transistors, triacs, diodes, thermistors, synodiodes. A diode allows current to flow in one direction only and blocks the reverse direction. We use them in rectifiers and power supplies. An SCR is like a diode with a gate control. It turns on only when it receives a small trigger signal, and it is used in controlled rectifiers and soft start circuits. A transistor works as a switch or amplifier. A small input controls a bigger output. Used in control boards and power supplies. A triac conducts in both directions on AC when triggered, and is used in dimmers and fan controllers. A diac is a small trigger device used to fire a triac at a set voltage. A thermistor is a temperature-sensitive resistor. NTC types drop resistance when heated, PTC types rise. Used for temperature sensing and soft start. A synodiode is designed to conduct backwards at a set voltage and is used for voltage regulation. Topic 18b. State that semiconductor devices are temperature sensitive and explain the methods of heat dissipation. Semiconductors are very sensitive to heat. Too much heat can damage their internal junctions. We remove heat using heat sinks, thermal paste, ventilation, fans or cooling plates. Keeping the device cool increases its life and reliability. Topic 18c. Explain that there is a possibility of damage occurring to semiconductor device during insulation resistance testing. Insulation resistance testers apply very high voltages, normally 500 to 1000 volts. Most electronic components cannot survive this. If left connected, the test voltage can punch through and destroy the semiconductor. So we must isolate or disconnect electronic parts before doing IR testing. Topic 18d. Give examples of the causes of transient voltages on power supply circuits and explain how these can be minimized to prevent damage to semiconductor devices. Transient voltages come from switching motors, inductive loads, lightning, supply disturbances and transformer switching. These short, sharp spikes stress semiconductor devices. We minimize them with surge arresters, MO versus snubber circuits, proper earthing and good wiring layout. Topic 18e. Explain the term peak inverse voltage with respect to semiconductor devices. Peak inverse voltage, PIV, is the maximum reverse voltage a semiconductor device can safely block. If the reverse voltage is higher than the PIV rating, the device can break down and fail. So we must isolate or disconnect electronic parts before doing IR testing. Topic 18f. Explain the differences between the semiconductor device and circuit conditions with respect to peak inverse voltage. The circuit produces a certain reverse voltage depending on the supply and rectifier design. The semiconductor must have a PIV rating higher than that circuit value. If the device rating is too low, it will fail under reverse voltage conditions. Matching device rating to circuit conditions is essential. Topic 18g. State that the PIV is referred to as VRM. On datasheets, PIV is listed as VRM, the maximum repetitive reverse voltage. It means the same thing as PIV. Topic 18h. Explain with the aid of diagrams the operation of a single diode as a half-wave rectifier. A half-wave rectifier allows only the positive half of the AC cycle to pass. The diode blocks the negative half. The output becomes a series of pulses, not full AC. Topic 18I. Explain with the aid of diagrams the operation of a single SCR as a controlled rectifier. An SCR turns on only when the gate receives a trigger. By changing the firing angle, we control how much of the AC waveform becomes DC. Earlier firing gives more output, later firing gives less. Topic 18J. Explain with the aid of diagrams full-wave rectification using different transformer and diode arrangements on a single-phase supply. Full-wave rectification uses both halves of the AC cycle. This can be done with a center-tapped transformer and 2 diodes, or a 4-diode bridge. The output is smoother because there are 2 pulses per cycle. Topic 18I. Explain with the aid of diagrams the operation of a single SCR as a controlled rectifier. An SCR turns on only when the gate receives a trigger. By changing the firing angle, we control how much of the AC waveform becomes DC. Earlier firing gives more output, later firing gives less. Topic 18K. Explain how a transistor is used, as a switch, as a common emitter amplifier. As a switch, the transistor is fully on or off depending on the base signal. As a common emitter amplifier, a small signal at the base produces a much larger signal at the collector. Topic 18L. Explain with the aid of a diagram how a triac controls the load current in an AC circuit. A triac fires at a chosen point in every half cycle. By changing this firing angle, it controls how much power reaches the load. This is how dimmers and speed controllers work. Topic 18M. Explain with aid of diagrams controlled full-wave rectification on a single-phase supply. Controlled full-wave rectification uses SCRs. The SCRs fire at selected angles on both halves of the AC cycle. This gives adjustable DC while using the full wave. Topic 18N. Explain with the aid of diagrams how 3-phase half and full-wave rectification can be achieved using diodes and a suitable transformer. 3-phase half-wave uses 3 diodes. 3-phase full-wave uses 6. The DC output is smoother because there are more pulses per cycle compared to single-phase. Topic 18O. Compare the output waveforms of all the above uncontrolled rectifiers in terms of smoothness of the output. Half-wave, roughest, 1 pulse per cycle. Single-phase full-wave, smoother, 2 pulses. 3-phase half-wave, 3 pulses, smoother again. 3-phase full-wave, 6 pulses, smoothest DC. More pulses equals less ripple. Topic 18P. State that capacitors, chokes and resistors are used for filtering the output of rectifier circuits. The DC output still contains ripple. We smooth it using capacitors to store charge, chokes to resist sudden changes, resistors to shape and discharge the filter network. Together these reduce ripple and clean the DC. Bringing it all together. Topic 18 helps us understand how basic electronic components work and why they are used in electrical systems. We learned how diodes, SCRs, transistors, triacs, diodes, thermistors and xenodiodes behave, and how temperature and transient voltages affect them. We also looked at PIV ratings, rectifiers, controlled circuits and filtering. Understanding these principles is essential for working safely with modern electrical equipment, because almost everything today contains electronics. Summary. Diodes conduct one way, SCRs and triacs control power. Transistors act as switches or amplifiers. Thermistors react to temperature, xenos regulate voltage. Semiconductors are heat-sensitive and need cooling. Insulation testing can damage electronics. Transients damage semiconductors, use surge protection. PIV, VRRM, must exceed circuit reverse voltage. Half wave equals rough DC, full wave equals smoother, three-phase equals smoothest. Filters, capacitors, chokes, resistors, smooth DC output. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we're learning Topic 19, the purpose and use of test instruments. This topic is essential for every electrician because safe and reliable electrical work depends on correct testing. We'll go through the common test instruments, what each one is used for, how to connect them correctly, the precautions you must take, and why correct instrument settings are critical before testing. By the end of this lesson, you should feel confident choosing the right instrument and using it safely in real installations. Topic 19a. Explain the purpose and give typical applications of the following types of test instruments. Insulation resistance tester. This instrument applies a high DC test voltage, usually 250 V, 500 V or 1000 V, to measure the insulation quality between conductors. We use it to check for damaged insulation, moisture, aging or installation faults. It ensures cables are safe before energizing a circuit. Voltmeter. A voltmeter measures the voltage between 2 points. We use it to check supply voltage, phase to neutral and phase to earth voltage, and to verify that circuits are isolated. Earth loop impedance tester. This tester measures the impedance of the earth fault loop. This tells us how quickly protective devices, like MCBs and RCDs, will trip during a fault. It ensures the installation meets disconnection time requirements. RCD tester. An RCD tester checks that an RCD trips within the correct time at the correct leakage current. We test at half, 1 times and 5 times rated current where required. This proves shock protection is working. Phase rotation meter. This instrument shows the sequence of the 3 phases, L1, L2, L3. Correct phase rotation is essential for motors, pumps and machinery. Ammeter. An ammeter measures current flowing in a circuit. Clamp meters let us measure current without disconnecting the conductor. We use it for load checks, fault finding and verifying maximum demand. Ohmmeter. An ohmmeter measures resistance in a circuit or component. We use it to check continuity, heating element resistance, bonding conductors and other low-resistance paths. Topic 19b. Explain how the above types of test instruments should be connected to test the circuit. Each instrument has a correct way to connect. Insulation resistance tester is connected with the circuit isolated and conductors separated. We test between active earth, active neutral and neutral earth. Voltmeter is connected in parallel across the 2 points where we want to measure voltage. Earth loop impedance tester is connected between active and earth at a socket outlet or test point. RCD tester plugs into an outlet or connects to the RCD test terminals to create a controlled leakage. Phase rotation meter connects to all 3 phases and displays the rotation order. Ammeter is connected in series, unless it is a clamp meter, which clamps around the conductor. Ohmmeter is used with the circuit de-energized, connected across the component being measured. The key rule is: never connect resistance or continuity testers to live circuits. Topic 19c. Detail any specific precautions required when using the above instruments. When using test instruments, we must follow strict safety precautions. Make sure the circuit is isolated when using insulation, continuity or resistance tests. Prove the tester works before and after use using a known source. Prove test prove. Check leads for damage, cracked insulation or exposed metal. Use the correct category rating, Cat 2, Cat 3, etc., for the environment. Keep hands clear of live parts and avoid touching metal probes. Ensure correct test voltage and range are selected. For clamp meters, only clamp one conductor at a time, not an entire cable. For earth loop tests, be aware that a small fault current is injected. Ensure no sensitive equipment is running. For RCD testing, expect the circuit to trip and reset afterwards. These precautions protect you and your equipment. Topic 19d. Explain the importance of ensuring that the correct connections, functions and range are selected on the test instrument before it is used to test a circuit. Selecting the correct function and range is essential because wrong settings can damage the instrument, for example, using resistance mode on a live circuit. Incorrect range can give false readings, which could lead to unsafe installations. Wrong connections can put dangerous voltage onto the wrong terminals, causing shocks, arc flashes or blown fuses. Testing with incorrect settings can fail to find genuine faults, such as insulation breakdown or incorrect polarity. Before testing, always check 3 things. 1. Correct function selected, voltage, resistance, current, IR test, loop test. 2. Correct range chosen, for example, AC volts, not DC. 3. Correct connections made to the circuit. This ensures testing is safe, accurate and compliant with AS/NZS 3000 requirements. Bringing it all together. To bring everything together, Topic 19 teaches us how to use the essential electrical test instruments safely and correctly. We learned the purpose of each tester, how to connect them properly, and the precautions needed to avoid damaging equipment or harming ourselves. We also covered why choosing the right function and range is critical for getting accurate and safe test results. Understanding these instruments is a core competency for every electrician, especially when verifying installations or troubleshooting faults. Summary. Insulation testers check insulation quality. Voltmeters measure voltage, connect in parallel. Earth loop testers measure fault loop impedance. RCD testers verify tripping current and time. Phase rotation meters check 3-phase sequence. Ammeters measure current, clamp meters avoid disconnection. Ohmmeters measure resistance, only use on dead circuits. Always use correct settings, ranges and connections. Safety precautions, isolation, correct leads, prove test prove, correct categories. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we are learning topic 20, testing of installations, appliances, and fittings, which is one of the key responsibilities of a licensed electrician. Every installation must be tested in a safe, logical, and methodical way before it is connected to supply. Testing is not optional. It is required by AS/NZS 3000, AS/NZS 3017, and the Electricity Safety Regulations. We will look at the complete testing process. How to prepare. What to check visually and mechanically. The sequence of mandatory tests. The instruments used. Acceptable values. Protecting fittings from damage during tests. Additional checks required for special installations. And the approval and certification requirements. Let's go through each part step by step. Topic 20a. Explain that an electrician should approach an installation for testing in both an orderly and logical manner. When approaching any installation for testing, the electrician must work in a structured and organized way. This means planning the testing sequence before starting, isolating the supply correctly, and ensuring the installation is safe to handle. Testing must follow a consistent order so that no part is missed. The recommended sequence starts with visual checks, then circuit identification, then dead tests, and finally live tests. Working in a logical order prevents confusion, reduces mistakes, and makes it easier to locate faults. Topic 20b. Explain that visual and mechanical checks of the installation are required by AS/NZS 3000 prior to instrument testing. Explain that this is done to ensure that all the specific requirements for issuing compliance certification are satisfied. Before any instrument is used, AS/NZS 3000 requires a full visual and mechanical inspection. This includes checking correct cable sizes, correct circuit protection, correct RCD placement, correct terminations, mechanical support for cables, correct identification, IP ratings of fittings, earthing continuity and bonding, and that equipment is undamaged and installed to standard. This step confirms that the installation meets the wiring rules and is ready for testing. A compliance certificate cannot be issued unless both the visual inspection and the tests meet the standard. Topic 20c. Explain the specific tests that are required by AS/NZS 3000 and state the test instrument type required to perform each of those tests. AS/NZS 3000 and AS/NZS 3017 specify the full set of mandatory tests. 1. Continuity of earthing conductors. O instrument, continuity tester or multifunction tester. 2. Continuity of protective bonding. O instrument, continuity tester. 3. Insulation resistance. O instrument, insulation resistance tester, 500V or 1000V depending on system. 4. Polarity. O instrument, continuity tester or multimeter. 5. Earth loop impedance, ELI-O instrument, earth loop impedance tester. 6. Prospective short circuit current, PSC-O instrument, PSC tester or ELI/PSC combined tester. 7. Verification of voltage drop. O instrument, calculation or measurement with multimeter. 8. RCD testing. O instrument, RCD tester, trip time and trip current testing. 9. Operational tests. O instrument, multimeter and functional testing devices. All tests must be completed for every new installation before connection. Topic 20d. Describe the methods of carrying out the tests specified in AS/NZS 3000 to 2007, stating the minimum and maximum values, where appropriate, that are acceptable. The methods and acceptable values include continuity of earthing and bonding. Reading must be low resistance, typically less than 1 ohm for bonding conductors. Insulation resistance. Minimum acceptable value, 1 megohm between all conductors. Many electricians aim for much higher values. Polarity. The active must be connected to the correct terminals of switches and protection devices. Neutral must not be switched. Earth must not be mixed with neutral. ELI values must be low enough so the protective device will disconnect within the required time. Different device types have different maximum allowable loop impedances. RCD trip times. O rated current, 30 mA, must trip within 300 milliseconds. O at 5 times rated current must trip within 40 milliseconds. Prospective short circuit current must be within the breaking capacity of protective devices. Voltage drop must not exceed 5% total from the point of supply to the equipment. Testing must be carried out exactly as described in AS/NZS 3017. Topic 20. Explain that specific installations have additional checks and test requirements as prescribed in the companion standards listed in Schedule 2. Some installations need extra checks beyond the /NZS 3000. These include medical locations, hazardous areas, swimming pools, explosive atmospheres, temporary construction sites, and marinas. Schedule 2 lists the companion standards, such as /NZS 3003 for hospitals and /NZS 60079 for hazardous areas, each containing extra test requirements. These ensure the installation is suitable for high-risk environments. Topic 20F. Take that Regulation 70 specifies the installation work requiring inspection by a registered electrical inspector prior to connection to the power supply. Regulation 70 of the Electricity Safety Regulations lists the work that must be inspected by a registered electrical inspector before connection. This includes mains work, main switchboard work, meter board work, work in medical or hazardous locations, large capacity installations, and high-risk electrical work. The electrician cannot connect these installations, they must wait for inspection approval. Topic 20G. Take that all the tests of installation wiring work as detailed under Regulation 65 and certification for compliance Regulation 66 to 69 must be completed before connection to a power supply. Regulations 65 to 69 require all testing and all certification to be completed before connecting an installation to supply. The electrician must complete all mandatory tests, complete the visual inspection, complete the Certificate of Compliance, COC, complete the Electrical Safety Certificate, ESC, and only then connect the supply. Topic 20H. Detail and identify those fittings that form part of the installation which may be damaged by test voltages. Some fittings can be damaged by high-voltage insulation tests. These include LED fittings, electronic ballasts, electronic dimmers, surge protection devices, control circuits with sensitive electronics, smoke alarms, and some appliances left connected. These must be disconnected or isolated before insulation testing. Topic 20. Explain the methods by which fittings can be either disconnected from the circuit under test or shorted out to prevent damage from the test voltages. To protect sensitive equipment during insulation testing, electricians can disconnect the fitting completely, remove lamps, control modules or drivers, isolate the circuit at a terminal block, short active and neutral together and test between and to earth, or test the wiring before connecting any equipment. This prevents damage to electronics. Topic 20J. Take the requirement that approvals are required before equipment can be connected to a power supply. Some equipment must have formal approval before it can be connected. Examples include mains equipment, metering equipment, main components, supplier authority equipment, and hazardous area equipment. Only after approval can the electrician connect the installation to the supply. Topic 20K. Take that following repairs electrical appliances must be tested to ensure they are safe in accordance with the requirements of /NZS 5762, Regulation 92. After repairing an appliance, it must be retested according to /NZS 5762. Regulation 92 requires that the appliance is proven electrically safe before returning it to service. This includes an insulation test, earth continuity, polarity, and an operational test. Bringing it all together. Topic 20 brings together the complete process of testing an electrical installation safely and correctly. Testing starts with planning and visual inspection, then moves through the full list of required tests using the correct instruments and following the correct sequence. The topic explains acceptable values, how to avoid damaging fittings, and when additional checks or inspections are required under the regulations. To finish the job legally, all testing and certification must be completed before an installation is connected to supply. Understanding this topic ensures that every installation meets /NZS 3000 in the ESRs, and that the work is safe for the customer and compliant with New Zealand law. Summary. Testing must follow a logical order and be well planned. Visual and mechanical checks are required before instrument testing, as/NZS 3000 and as/NZS 3017 specify all mandatory tests. Key tests include continuity, insulation resistance, polarity, ELI, PSC, RCD tests, and operation. Sensitive fittings must be protected from insulation test voltages. Special installations require additional testing under companion standards. Regulation 70 lists work requiring inspection by an electrical inspector. All tests and certification must be completed before connection. Approvals are required for certain equipment before energizing. Repaired appliances must be tested to as/NZS 5762. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we're learning Topic 21, Testing, Inspection, and Certification, which is one of the most important parts of the electrical regulations. This topic explains who can test, who can certify, what work requires inspection, and what the law requires under the Electricity Safety Regulations 2010. Understanding this topic is essential, because every electrician must know what paperwork is required, who signs what, and what tests must be carried out before an installation can be connected to supply. Let's go through each subtopic clearly and simply. Topic 21A. Define the terms testing, certification and inspection as prescribed in Schedule 1 of the Electricity Safety Regulations 2010. Let's define the three key terms. Testing means doing the physical electrical tests required by as/NZS 3000 to confirm that installation work is electrically safe. This includes insulation resistance, polarity, earth continuity, earth fault loop impedance, RCD tests, and functional checks. Certification means completing the correct legal documentation, COC and ESC, to show the work is electrically safe and complies with the regulations and relevant standards. Inspection means an independent check of prescribed electrical work by a registered electrical inspector, not the electrician who did the job. Some installation work must legally be inspected before connection. These three steps, testing, certification, and inspection, work together to keep installations safe and legally compliant. Topic 21B lists the types of installation work requiring testing and certification by a registered electrician before connection to the supply. Under the ESRs, a registered electrician must test and certify any prescribed electrical work that forms part of a new installation. Any work altering an installation, such as adding circuits, submains, or rewiring. Any mains work, including mains upgrades, relocations or replacements. Any work where supply is being reconnected after repair or alteration. Before supply can be turned on, the electrician must complete black tick mark emoji, all required tests. Black tick mark emoji, a certificate of compliance, COC. Black tick mark emoji, an electrical safety certificate, ESC. This applies to almost all installation work except the tasks listed as low risk in Schedule 1. Topic 21C lists the types of installation work which can only be inspected by a registered electrical inspector. Some installation work is classed as high risk and must be inspected by a registered electrical inspector. Examples include mains switchboard upgrades, mains work involving earthing or bonding, works that affect safety of main systems, installations in hazardous areas, medical cardiac locations, any work requiring certification that the main system is correct. The electrician does the work and does the tests, but the inspector must independently check and sign off the job before it can be connected. Topic 21D lists the installations that are subject to periodic inspections by electrical inspectors. Certain installations must be inspected regularly because they involve higher levels of risk. These include marinas and caravan parks, shows and carnivals, construction sites, medical treatment areas, large commercial or industrial installations with special requirements. These sites need ongoing inspection to ensure continued electrical safety. Topic 21e. Explain who is responsible for performing the prescribed tests associated with the completion of the compliance documentation involving self-certification and work requiring inspection. There are two responsibilities here. Self-certification. This is when the electrician can test and certify the job themselves. They must do all testing and complete both the COC and ESC. Work requiring inspection. The electrician still carries out all required tests, but a registered electrical inspector must confirm the work is safe and compliant. The inspector performs their own checks and signs the inspection part of the documentation. The electrician is always responsible for doing the installation correctly, even when an inspector is involved. Topic 21f. Understand that certifying prescribed electrical work means that the work is electrically safe and has been tested in accordance with the standards cited in the regulations, and that it has been carried out in accordance with the standards cited by the regulations. When an electrician signs a COC, they are legally declaring that the work is electrically safe. All tests required under AS/NZS 3000 have been completed and passed. The work complies with all standards that the ESRs reference. The installation is safe to connect to a power supply. Signing a COC is a serious legal obligation. The person signing takes full responsibility for the safety and compliance of the work. Topic 21g. Describe how the tests for compliance are performed and state the values which are acceptable. Compliance tests include continuity of earthing, must be low resistance. Insulation resistance, minimum 1 megohm at 500 V for LV circuits. Polarity, active, neutral, earth connected in the correct places. Earth fault loop impedance, must be low enough to operate protection. RCD testing, must trip in required times. Functional testing, switches, isolators, protection devices must work. These tests must be done in the correct order from AS/NZS 3000. Topic 21h. Understand that the certificate of compliance must be completed as soon as practicable and no later than 3 days after the work is completed, and copies must be supplied and retained. The law requires the COC must be completed as soon as practicable and within 3 days of finishing the work. A copy must be given to the customer within 20 days. The electrician must keep a copy for 3 years. A copy must be supplied to the EWRB within 20 working days if requested. These time frames are legal requirements and must be followed. Topic 21. I state that wiring installation work is subject to audit by the Electrical Workers Registration Board to ensure worker competency. All installation work done by electricians can be audited by the EWRB. This ensures the work meets safety standards. Electricians remain competent. Records and certification are correct. If work is unsafe or non-compliant, the board can require retraining or take disciplinary action. Bringing it all together. To bring everything together, Topic 21 explains the legal steps that every electrician must follow to ensure installation work is safe. We learned the difference between testing, certification, and inspection, and the responsibilities of both electricians and inspectors. We also covered when certification is required, when inspection is required, and what the law demands for COCs and documentation. Understanding Topic 21 ensures you work legally, safely, and professionally. Summary. Testing confirms electrical safety under AS/NZS 3000. Certification includes COC and ESC requirements. Some work must be inspected by a registered electrical inspector. High-risk installations require periodic inspections. Electricians test all work, inspectors verify high-risk work. COCs must be completed within 3 days and retained for 3 years. EWRB may audit installation work at any time. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whit Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Topic 22, all about three-phase motors, how they are built, how they work, and how we start and protect them. Three-phase motors are used everywhere in industry, so this topic is essential for both exam questions and real-world electrical work. First, we look at the motor construction, the rotor, stator windings, and the iron circuit. Then we move into the operating principles, the rotating magnetic field, synchronous speed, slip, torque, and the effects of different supply conditions. Finally, we cover motor starters, DOL, star delta, autotransformer, and soft starters, along with the protection they provide. By the end of this topic, you'll understand how a three-phase motor is built, how it behaves, and how to start and protect it safely. Topic 22.1a. Describe the components of a three-phase induction motor. 1. Rotor, including differences between cage and wound types. The rotor is the rotating part of the motor. When the magnetic field from the stator rotates, the rotor is pulled around with it, producing torque. There are two common rotor types. Squirrel cage rotor. This is the most common type. It has aluminium or copper bars running along the length of the rotor. These bars are short-circuited at each end by end rings. It looks like a squirrel cage, which is why it gets that name. There are no windings, no slip rings, no brushes. It is very robust, low maintenance, and suitable for most industrial loads. Wound rotor, slip ring rotor. This type has proper three-phase windings on the rotor. The ends of the rotor windings connected to slip rings. External resistors can be connected through brushes to provide variable resistance in the rotor circuit. This allows high starting torque, smooth speed control, better performance for heavy load starts. However, it is more expensive, requires more maintenance. Slip rings and brushes wear out over time. So in simple terms, cage rotors equals simple, strong, common. Wound rotors equals adjustable performance but higher maintenance. 2. Stator windings. The stator is the fixed part of the motor. It contains 3 sets of windings arranged 120 degrees apart. When we apply a three-phase supply to the stator, these windings produce a rotating magnetic field. The windings are placed into slots in the stator iron. They are insulated tight and varnish treated to protect them against heat, vibration, and moisture. The stator windings determine motor voltage rating, motor connection method, star or delta, motor power rating. They must be sized correctly so that the motor can handle full load current without overheating. 3. Iron circuit. The iron circuit is made from thin laminated steel sheets, stacked together to form the stator core, the rotor core. Laminations are used to reduce eddy current losses. The iron circuit provides a low resistance path for the magnetic field, mechanical strength, channels, slots for the windings. Without the iron circuit, the magnetic field would be very weak, and the motor would have almost no torque. In short, the iron circuit is the magnetic backbone of the motor. Topic 22.1b. Describe the frame types and ventilation methods available, giving typical applications for each type. The motor frame protects the internal parts and provides mechanical mounting. Different industries require different frame types depending on the environment. Open drip proof, ODP, ventilation openings allow air to flow through, protected against falling objects and dripping water. Used indoors where dust is minimal. Totally enclosed fan-cooled, TEFC, no open ventilation holes. External fan blows air over the frame. Very common in workshops and industrial plants. Good for dusty or damp environments. Totally enclosed non-ventilated, TENV, no fan, no vents. Cooled only by the motor's surface area. Used in clean, quiet environments or hazardous area applications. Totally enclosed air over, TEAO, needs external airflow, like a duct or blower, used where motors are mounted inside ducts or equipment. Explosion-proof or flame-proof frames. Built to contain internal explosions. Used in hazardous areas such as fuel depots, chemical plants, dust risk environments. Ventilation summary. Motors can be cooled by open ventilation, forced ventilation, fans or blowers, surface cooling, enclosed cooling systems. Choosing the correct frame and cooling method is essential for reliability and safety. Topic 22.2a. Explain the principles of operation of a three-phase induction motor in terms of the stator rotating field, rotor currents and flux, relative motion between the rotating field and rotor and the direction of rotor rotation. A three-phase induction motor works because of a rotating magnetic field produced by the stator windings. Here's the sequence. 1. Stator rotating magnetic field. A three-phase supply feeds the stator windings. The three currents are 120 degrees apart. This creates a magnetic field that rotates smoothly around the stator. The speed of this rotating field is called synchronous speed. 2. Rotor-induced current. The rotor is not connected to the supply. The rotating field cuts across the rotor bars or rotor windings. This induces current in the rotor, Faraday's law. 3. Rotor magnetic field. The induced current in the rotor creates its own magnetic field. The interaction between the stator field and rotor field produces torque. 4. Rotor rotation. The rotor always turns in the same direction as the rotating stator field. It cannot reach synchronous speed because then no relative motion exists. The difference between synchronous speed and rotor speed is called slip. In short, stator produces a rotating field, field induces rotor currents, rotor magnetic field produces torque, rotor follows the field. Topic 22.2b. Define the terms. When we talk about induction motors, there are three key speeds you must understand. The first one is synchronous speed. This is the speed of the rotating magnetic field in the stator. It does not depend on the load. It only depends on the supply frequency and the number of poles in the motor. The formula is synchronous speed equals 120 times the supply frequency, divided by the number of poles. The answer is in revolutions per minute. So, for example, on a 50 Hz supply, a 4-pole motor has a synchronous speed of about 1500 rpm. The second idea is slip speed. Slip is simply the difference between the synchronous speed and the actual rotor speed. If the rotor ran at the same speed as the magnetic field, there would be no torque. So, slip must always exist for the motor to produce torque. We can express slip as a speed difference, or as a percentage. Slip speed equals synchronous speed minus rotor speed. Slip percentage equals the slip speed divided by synchronous speed, multiplied by 100. The third term is full load speed. This is the actual rotor speed when the motor is running at its rated load. Because slip must exist, the full load speed is always slightly lower than the synchronous speed. For example, if the synchronous speed is 1500 rpm, the full load speed might be around 1450 rpm. In this case, the slip is roughly 3.3%. That is how synchronous speed, slip, and full load speed all link together in an induction motor. Topic 22.2c. Draw a torque/speed characteristic graph to explain relationship between slip, Ns and Nr. Source: Electrical Academia, Induction Motor Torque Speed Characteristics, Access 2025. Imagine a graph with speed on the horizontal axis and torque on the vertical axis. At synchronous speed, torque is 0 because slip is 0. As slip increases, speed drops slightly, torque increases. At full load speed, torque is at the rated operating level. At high slip, low speed, the torque peaks, called breakdown torque. Beyond this point, if the motor slows further, torque falls sharply. This curve shows how torque depends on slip. Topic 22.2d. Explain the effect that a reduction in supply voltage has on the line currents of a loaded induction motor. If voltage drops, the motor produces less magnetic flux. To produce the same torque, the rotor must draw more current. Line current increases significantly. The motor heats up faster and may trip over load protection. In simple terms, low voltage equals high current equals overheating risk. Topic 22.2e. Explain the effects on a three-phase induction motor if one supply line is open-circuited on 1. Star-connected motor, 2. Delta-connected motor. Star-connected motor. With one phase open, the motor only receives an incomplete rotating field. Torque drops heavily. Motor vibrates, overheats, and may stall. Starting is usually impossible. Delta-connected motor. The motor may still run because each winding is connected across two phases. However, current becomes unbalanced. Motor overheats quickly. Severe loss of torque occurs. In both cases, prolonged operation is dangerous. Topic 22.2f. Explain the effects on a three-phase induction motor if one of the stator windings is reversed. If one stator winding is reversed, the three-phase sequence is broken. The rotating magnetic field collapses and is no longer uniform. The motor may not start. If it does start, it will vibrate and overheat. It produces almost no torque and is unsafe to run. This is a common wiring mistake after repairs. Topic 22.2g. Explain how the winding reversal problem may be diagnosed and rectified. To diagnose: motor hums but does not rotate. High current draw. Severe vibration. Rotor may twitch but not spin. To fix: check the phase sequence. Identify the reversed winding by continuity and phase marking. Swap the incorrect connection so all windings follow the same phase order. Topic 22.2h. Explain the effect of load on an induction motor's PF and efficiency. As load increases, power factor improves, moves closer to unity. Efficiency increases up to a point. At very light load, both PF and efficiency are poor. Induction motors operate best near their rated load. Topic 22.21. Explain how capacitors are connected to three-phase induction motors to correct the power factor and to reduce line current. Capacitors supply reactive power locally. By adding capacitors, the motor draws less reactive power from the supply. Line current decreases. Power factor improves. System losses reduce. Capacitors are usually installed at the switchboard or motor starter. Topic 22.2j. Explain how. 1. The direction of rotation is changed in a three-phase induction motor. 2. The windings of a three-phase motor may be connected in either star or delta, and the effects on voltage rating and power produced. 1. Changing motor direction. Swap any two of the three supply phases. The rotating magnetic field reverses, so the rotor follows. 2. Star versus delta connections. Star. O used for high voltage supply. O lower current in each winding. O lower starting torque. Delta. O used for lower voltage supply. O higher current in windings. O higher torque and higher power output. Some motors use star-delta starters to reduce starting current. Topic 22.2k. Explain the difference between starting current and run current for a three-phase induction motor and how they may be calculated. Starting current. Very high, typically 5 to 8 times the full load current. Occurs because rotor is stationary, slip equals 1. High inrush current flows. Run current. Normal operating current at full load, much lower than starting current. Calculations use motor ratings, kW, voltage, efficiency, and PF. 22.2l. Solve problems involving three-phase induction motors. In this part of the topic, we look at the key formulas you will need for exam problems involving motors. These formulas help you calculate power, speed, slip, and torque. First, true power. True power is calculated using voltage, current, the square root of 3, and the power factor. So the formula is P equals V times I times root 3 times power factor. The answer is in watts. Next is reactive power. Reactive power uses the same idea, but instead of power factor, we use the sine of the phase angle. So the formula is Q equals V times I times root 3 times sine of the angle. This is measured in bars. Then we have apparent power. Apparent power is simply voltage multiplied by current multiplied by root 3. This gives you volt amps. We also have the formula for synchronous speed. Synchronous speed equals 120 times the supply frequency, divided by the number of poles. The answer is in revolutions per minute. Slip percentage is another important value. Slip percentage is worked out by taking the difference between synchronous speed and rotor speed, dividing that by synchronous speed, and then multiplying by 100. This tells you how much the rotor is lagging behind the magnetic field. Finally, we have the torque formula. Torque equals 9.55 times the output power divided by the speed in revolutions per minute. This formula helps you understand how much turning force the motor is producing. Understanding these formulas makes it much easier to calculate motor performance in exam questions. Topic 22.3, Three-phase motor starters. 22.3a, describe the protection a motor starter may provide and explain how this may be achieved. A motor starter does more than just turn a motor on and off. It usually provides several types of protection. 1. Overload protection. Protects the motor from drawing too much current over time. Achieved using thermal overload relays, electronic overloads, or thermal magnetic devices. They trip when the motor heats up due to being overloaded or jammed. 2. Short circuit protection. Achieved using fuses or circuit breakers upstream from the starter. These devices operate instantly on very high current faults. 3. Phase failure protection. If one phase is lost, the motor will overheat quickly. Some overload relays detect the unbalance and trip early. 4. Undervoltage, no-volt protection. Prevents automatic restart after a power failure. Achieved using an electromagnetic contactor coil that drops out when voltage falls. 5. Isolation. Starters include a manual isolator or are installed with one, allowing safe maintenance. Together, these functions keep the motor safe electrically and mechanically. Topic 22.3b, describe how phase reversal protection can be provided. Phase reversal protection stops a motor from running in the wrong direction. This can be provided by 1. Phase sequence relays. They monitor the order of the three-phase supply. If the phases are reversed, the relay prevents the contactor from energizing. 2. Control wiring design. Some starter circuits use interlocked reversing contactors. Only one direction can be selected at a time. Electrical and mechanical interlocks prevent accidental phase swapping. Phase reversal protection is commonly required for equipment that must always rotate in the correct direction, such as pumps, conveyors, and compressors. Topic 22.3c, describe the operation of a DOL starter. Give advantages, disadvantages, and applications for DOL starters. A direct online, DOL, starter connects the motor directly to the supply when the contactor is energized. How it operates. Pressing the start button energizes the contactor coil. The contactor pulls in, connecting the motor straight to the full line voltage. Overload relay is in the line to protect against overload. Pressing stop de-energizes the contactor and the motor stops. Advantages. Simple design. Reliable. Low cost. Easy to maintain. Strong starting torque. Disadvantages. Very high starting current, typically 5 to 8 times full load current. Causes mechanical shock. Causes voltage dips on weak or rural networks. Not suitable for large motors. Applications. Small motors, generally under 4 to 5 kilowatts depending on the supply. Fans, small pumps, workshop machines, small compressors. Topic 22.3d. Explain why reduced voltage starting is required in some installations, including advantages and disadvantages. Large motors draw very high starting current when started. This can cause voltage dips that affect other equipment. Stress mechanical couplings. Trip protective devices. Reach network connection rules. To prevent this, reduced voltage starting is used. Advantages: lower starting current. Reduced mechanical shock on the driven equipment. Less strain on the supply network. Smoother acceleration. Disadvantages: lower starting torque. More complex and more expensive equipment. Not suitable for high torque starting loads unless properly designed. Reduced voltage starting is often required by the electricity distributor for motors above certain kW levels. Topic 22.3e. Describe the operation of the following types of reduced voltage starters, including advantages, disadvantages and applications. 1. Star-delta starter. Operation. Motor starts in star. Each winding receives only line/3 voltage. Starting current and torque are reduced. After acceleration, the timer switches the windings to delta, allowing full voltage and full torque. Advantages. Simple and cost-effective. Good reduction in starting current. Disadvantages. Starting torque is reduced to 1/3 of DOL torque. Produces a current surge during star-delta transition. Motor windings must be suitable for star-delta. Applications. Motors where the load can start easily. Fans, blowers, centrifugal pumps. 2. Auto-transformer starter. Operation. Uses a tapped auto-transformer to supply the motor with a reduced voltage during start. After acceleration, the motor is switched to full line voltage. Advantages. Best reduction in starting current compared to other methods. Higher starting torque than star-delta. Disadvantages. More expensive and bulky. More complex wiring. Applications. Large motors that require higher starting torque, compressors, crushers. 3. Primary resistance starter. Operation. Resistances are inserted in series with each phase to reduce voltage during start. Resistors are bypassed once the motor speeds up. Advantages. Simple design. Smooth acceleration. Disadvantages. Resistors waste energy as heat. Limited starting torque improvement. Rarely used today. Applications. Older installations. Slip ring motor starting systems. 4. Electronic starters. For example, soft starters, wave chopping types. Operation use semiconductor devices, thyristors, to gradually increase the applied voltage. Provide smooth, controlled acceleration with minimal electrical disturbance. Advantages: very smooth starting. Excellent reduction in mechanical stress. Adjustable start parameters. No switching surges. Disadvantages: more expensive than star-delta. Produces some harmonic distortion. Applications: pumps, conveyors, HVAC systems, modern industrial motors. Bringing it all together. To bring everything together, Topic 22 teaches us the full picture of three-phase motors, from how they are built, to how they operate, to how we start and protect them. We first looked at the construction, the rotor, stator, and iron circuit. These physical components create the magnetic environment the motor needs. Then we explored the principles of operation, the rotating magnetic field, slip, synchronous speed, torque, and the effects of different supply conditions. This part showed us why motors behave the way they do and how to interpret their performance. Finally, we looked at starters, the practical side of installing motors. We saw how different starting methods reduce starting current, how phase reversal protection works, and how modern electronic starters improve control and reduce stress on the motor. Once you understand construction, principles, and starters together, you can diagnose faults, select the right starter, understand performance, and install motors safely and confidently. Summary. Three-phase motors use a rotating magnetic field to produce rotation. Key motor parts: rotor, stator windings, iron circuit. Cage rotors are simple and robust. Wound rotors allow external resistance control. Synchronous speed depends on frequency and number of poles. Slip is needed for torque production. Slip increases as load increases. Full load speed is slightly below synchronous speed. Torque speed curves show how motors behave from start to full load. Voltage drops increase current and reduce torque. Open circuit conditions in star or delta affect current, torque, and vibration. Reversing motor rotation is done by swapping any two phases. Star and delta connections affect voltage, current, and torque. Motor starters protect against overload, phase failure, and reversal. Dole starters are simple but have high starting current. Star delta, auto transformer, and primary resistance starters reduce starting current. Electronic starters give soft starting and better motor protection. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we are learning Topic 23, Single-Phase Motors, an important section of the Electrician Theory program. Most small appliances and tools in homes and small workshops run on single-phase motors, so understanding how they work, how they start, their types, advantages, disadvantages, and applications is essential. We will start with how a single-phase supply can produce a rotating magnetic field, then we will look at phase splitting for starting torque. After that, we will go through all the major types of single-phase motors and their construction and operation. Finally, we'll look at speed control for universal motors and where these motors are commonly used. Let's get into it. Topic 23.1, Single-Phase Induction Motor Operation. A. Explain how a single-phase supply can be used to provide an alternating magnetic field. A single-phase supply normally creates an alternating magnetic field, not a rotating one. The magnetic field simply swings back and forward as the AC supply changes direction. This alternating field cannot start a motor on its own because it does not naturally produce rotation. It just vibrates the rotor. However, once the rotor is already moving, the alternating field can keep it turning due to induction in the rotor. This is why extra starting systems are needed. Topic B. Explain how phase splitting can be used to provide starting torque in a single-phase motor. To create starting torque, we need a rotating magnetic field. Single-phase motors achieve this using phase splitting. Phase splitting means adding a second winding, start winding, that is intentionally made out of phase with the main winding. This can be done by resistance, split-phase motor, a capacitor, capacitor start, capacitor run, PSC, etc. This phase difference creates two magnetic fields, spaced in time. Together they appear like a rotating magnetic field, allowing the motor to start turning. Once the motor reaches speed, the start winding may be disconnected in some designs, or remain connected in PSC and capacitor run motors. Topic 23.2, Types of Single-Phase Induction Motors. A. Describe the operation and construction of the following types of single-phase induction motors. Now we look at each major type of single-phase induction motor. For each one, we explain its construction, operation, advantages, disadvantages, and applications. 1. Split phase, resistance start construction. 2 windings, main winding plus start winding. Start winding has higher resistance. Uses a centrifugal switch to disconnect the start winding. Operation. The high resistance start winding creates a phase shift when starting, giving moderate starting torque. Once the motor reaches roughly 70 to 80% speed, the centrifugal switch opens and removes the start winding. Advantages. Simple. Low cost. Reliable. Disadvantages. Low starting torque. Not suitable for heavy loads. Applications. Small tools, fans, blowers. 2. Capacitor start. Construction. Main winding. Start winding. Large start capacitor. Centrifugal switch. Operation. The capacitor creates a strong phase shift, giving a high starting torque. After the motor starts, the switch disconnects the capacitor and start winding. Advantages. Very high starting torque. Disadvantages. More complex. More expensive. Applications. Compressors, pumps, small workshop machines. 3. Permanently split capacitor, PSC capacitor start and capacitor run. Construction. 2 windings. 1 permanent capacitor in series with the auxiliary winding. No centrifugal switch. Operation. The capacitor stays in the circuit at all times, providing smooth running and better efficiency. Advantages. Quiet. Reliable, no switch, good running efficiency. Disadvantages. Lower starting torque than capacitor start. Applications. Fans, air handlers, blowers. 4. Capacitor start, capacitor run, dual value capacitor. Construction. 2 capacitors, a large start capacitor plus a smaller run capacitor. Centrifugal switch. Start winding plus run winding. Operation. The big capacitor gives very high starting torque. When speed is reached, the large capacitor disconnects but the smaller run capacitor remains. Advantages. Excellent starting torque. Smooth running. High efficiency. Disadvantages. Higher cost. Applications. Heavy-duty single-phase loads like pumps, refrigeration units. Topic B. Explain how external start relays may be used to start single-phase induction motors. Some motors use start relays instead of centrifugal switches. A start relay detects the motor current or back EMF, connects the start winding during starting, disconnects it once the motor is up to speed. Advantages. No moving parts in the motor. Suitable where centrifugal switches may clog or fail. Disadvantages. Extra component to install. Relay contacts can wear. Applications. Small refrigeration compressors, appliances with sealed motors. Topic 23.3. Additional single-phase motors. A. Explain the operation and construction of the following types of single-phase motors. Now we look at 3 additional common single-phase motor types. Universal motor construction, wound stator and rotor, brushes and commutator, can run on AC or DC. Operation. Because the stator and rotor currents reverse together, the motor still produces torque on AC. Advantages. Very high speed. Very high power to size ratio. Disadvantages. Brushes wear. Noisy. Applications. Drills, grinders, vacuum cleaners, kitchen appliances. Shaded pole motor construction. Simple stator with 1 winding. Copper shading rings on part of the pole. Squirrel cage rotor. Operation. The shading ring delays the magnetic field on part of the pole, creating a weak rotating field. Advantages. Very cheap. Very reliable. No start switch. No capacitor. Disadvantages. Very low starting torque. Poor efficiency. Applications. Desk fans, small blowers, fridge evaporator fans. Synchronous motor construction. Rotor with permanent magnets or a coil. Stator with single-phase AC winding. Often includes an auxiliary winding or capacitor. Operation. Starts like an induction motor, then locks into synchronous speed once rotor magnet field aligns. Advantages. Very accurate speed. Runs cool and efficient. Disadvantages. Low starting torque. Needs auxiliary starting method. Applications. Clocks, timing motors, microwave turntables. Topic B. Explain methods of speed control for universal motors and state typical applications where universal motor speed control is employed. Universal motors can be easily speed controlled because they use brushes. Common speed control methods. Variable resistors. Electronic controllers, TRIAC or SCR based, PWM control in modern tools. We used drills, routers, blenders, mixers, Vacuum cleaners. These appliances need variable speed for different jobs, and universal motors are ideal for this. Bringing it all together. Single-phase motors play a huge role in domestic and light commercial equipment. We learned how a single-phase supply produces an alternating magnetic field, and how phase splitting creates the rotating field needed for starting. We covered all major motor types, how they operate, their advantages, disadvantages, and applications. Then we looked at additional motors like universal, shaded pole, and synchronous motors, and how universal motor speed control works. This topic gives you the foundation to recognize different motor types on site, select the right motor for an application, and troubleshoot common problems. Summary. A single-phase supply produces an alternating field, phase splitting creates starting torque. Split-phase motors use resistance in the start winding. Capacitor start motors provide high starting torque. PSC motors run smoothly and quietly with a permanent capacitor. Capacitor start-run motors give both high starting torque and high efficiency. Start relays can replace centrifugal switches. Universal motors run on AC or DC and give high speed. Shaded pole motors are cheap but low torque. Synchronous motors run at constant speed. Universal motors are easy to speed control and common in hand tools. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we're looking at why electric motors need protection, what can go wrong, and how different protection devices keep motors safe. Motors deal with electrical load, mechanical load, and supply conditions, so if anything goes outside normal limits, the motor can be damaged very quickly. Good motor protection prevents breakdowns, fire risks, expensive repairs, and unsafe situations. We'll cover the common faults motors face, how thermal and magnetic overloads work, other protection systems like phase failure and thermistors, and finally what backup protection and discrimination mean in motor circuits. Topic 24a. Explain why electric motors may require protection against excess current. Motors draw more current when overloaded or jammed. Excess current heats the windings, breaks down insulation, and can destroy the motor. Protection trips the motor before overheating becomes severe. Mechanical overload. When the driven machine jams or becomes too heavy, the motor slows, draws high current, and overheats. Overload protection stops the motor before damage occurs. Undervoltage. If supply voltage drops, the motor slows and draws more current trying to maintain torque. This causes overheating. Undervoltage protection disconnects the motor and prevents automatic restart when power returns. Phase failure. If one phase of a three-phase motor is lost while running, the motor tries to run on two phases. Current rises sharply, torque drops, and the motor overheats fast. Phase failure relays detect this and trip the circuit. Phase reversal. If two phases are swapped, the motor runs backwards. This can damage pumps, conveyors, fans, and machinery designed for one direction. A phase sequence relay blocks the motor from starting if phase order is incorrect. Topic 24b. Describe the construction and operating principle of both thermal and magnetic overload units. 1. For three-phase motors. 2. For single-phase motors. Thermal overloads, three-phase and one-phase. Built using bimetal strips that bend when heated by motor current. Motor current flows through heaters inside the overload. If current stays too high for too long, the strip bends and opens a contact. This breaks the control circuit, dropping the contactor and stopping the motor. Works well for long-term overloads and slow heating faults. For three-phase motors, the overload senses all three phases so it detects imbalance or single phasing. For single-phase motors, it monitors the active conductor. Magnetic overloads, instantaneous trips. Use an electromagnetic coil that reacts quickly to very high currents. If a short circuit or severe fault current occurs, The magnetic force pulls open the trip mechanism instantly. They protect against short circuits but not long-term overloads. Most motor starters use both systems together, magnetic for short-circuit protection and thermal for overload. Topic 24c. Explain the use of the following protective systems. 1. Phase failure. 2. Phase reversal. 3. Thermistor. Phase failure protection. A relay monitors all three phases. If any phase voltage drops or is lost, the relay trips immediately. This prevents overheating and prevents the motor from single-phasing. Phase reversal protection. A phase sequence relay checks the incoming phase order. If the order is wrong, the relay blocks the contactor coil so the motor cannot start in reverse. Thermistor protection. Thermistors, PTC sensors, are embedded inside the motor windings. If temperature rises above a safe limit, the thermistor's resistance jumps sharply, triggering the protection relay, which opens the control circuit and stops the motor. This protects the motor from overheating caused by overload, ventilation issues, high ambient temperature or bearing failure. Topic 24d. Explain backup protection and discrimination with respect to protecting motor circuits. Backup protection. Backup protection is a second protective device that operates if the first one fails or cannot clear the fault. For example, if an overload relay trips too slowly during a short circuit, the upstream circuit breaker must trip to protect the cable and motor. Discrimination. Selectivity discrimination is making sure that only the device closest to the fault trips. This prevents unnecessary shutdown of the whole system. Example. A motor overload relay should trip for a motor overload. The main circuit breaker should stay on unless there is a severe fault like a short circuit. Correct discrimination keeps the rest of the installation running safely. Bringing it all together. Motor protection is all about preventing unnecessary damage and keeping the installation safe. Motors face electrical risks like excess current, undervoltage, phase failure and phase reversal, as well as mechanical risks like overload and stress. Thermal and magnetic overloads offer strong protection against different types of faults, while phase failure relays, thermistors and undervoltage devices prevent dangerous running conditions. Backup protection and discrimination ensure faults are cleared safely and only the right protective device trips. Understanding these principles helps electricians select the correct protection for every motor installation. Summary. Motors need protection from excess current, overload, undervoltage, phase failure and phase reversal. Thermal overloads protect against long-term overload heating. Magnetic overloads react instantly to short circuits. Phase failure and phase sequence relays protect against supply problems. Thermistors detect actual winding temperature. Backup protection ensures a second device clears the fault if the first one fails. Discrimination ensures only the closest protective device trips. Correct protection prevents costly damage in unsafe situations. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whit Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. In the last few topics, we've been working our way through motors, single-phase motors, three-phase motors, and motor protection and starters. We focused on how motors convert electrical energy into mechanical energy, and how we control and protect them in real installations. Now we're moving to the opposite side of the energy process. Instead of motors consuming electricity, we're looking at machines that produce electricity. Today we're starting topic 25, alternators. This topic is all about understanding how AC electricity is generated, what components make up an alternator, the different types of rotors and prime movers, and how three-phase generation works. We also look at the important relationship between frequency, poles, and rotational speed, something you'll use again and again, both in theory exams and in real-world work with generators. All right, let's get into it and go through the subtopics one by one. Topic 25a. Explain the basic construction of an alternator. An alternator is built around three essential parts. 1. A magnetic field. This field can be produced by permanent magnets, but in large alternators it is produced by DC field windings. 2. A conductor, armature windings. These windings are arranged so that they cut through the magnetic field. 3. Relative motion. Voltage is only induced when the magnetic field and the conductor move relative to each other. There are two common ways this construction is arranged. Rotating armature construction. The output windings, armature, rotate. The magnetic field is stationary. Slip rings and brushes carry the generated electricity away. This design is usually used for small machines. Rotating field construction. The magnetic field rotates. The output windings are fixed in the stator. Only a small DC current needs slip rings. This is the standard design for large alternators such as those used in the electricity network. Three-phase, polyphase, stator. Three sets of windings are positioned 120 degrees apart. As the magnetic field rotates, each set of windings produces a voltage waveform. These three waveforms are 120 degrees apart, creating the three-phase system used in industry and power distribution. Topic 25b. Describe and explain the various types of commonly used rotors. Alternators mainly use two rotor designs. Salient pole rotor. Has projecting magnetic poles. Salient means sticking out. Used in slow-speed machines. Suitable for machines that require many pole pairs, such as hydro generators and wind turbines. Cylindrical, non-salient, rotor. Smooth, solid body designed for strength. Used in high-speed machines like steam turbine alternators. Usually only 2 or 4 poles because the rotor must remain mechanically strong at high speeds. The choice of rotor type depends on the operating speed and type of prime mover. Topic 25c. Describe the types of prime movers. A prime mover is the machine that provides the mechanical energy to spin the rotor. Common prime movers include 1. Water turbines, hydro, use falling or flowing water. Very common in New Zealand. 2. Steam turbines driven by steam from coal, geothermal, or industrial boilers. 3. Gas turbines similar to jet engines. Used for peak load or emergency generation. 4. Diesel engines used for backup generators, rural sites, and portable generation. 5. Wind turbines. Wind turns the blades, which turn a generator through a gearbox or direct drive system. Each prime mover affects the alternator speed and therefore the frequency. Topic 25d. Explain the basic principles of AC generation. Three-phase. Three-phase AC is created when 1. The rotor produces a rotating magnetic field. 2. This field cuts across the stator windings. 3. The changing magnetic flux induces AC voltage in each winding. To create three-phase, the stator has 3 windings, spaced 120 degrees apart. As the rotor spins, each winding reaches peak voltage at different times. This produces 3 sine waves, 120 degrees apart. Three-phase generation is used because it is more efficient for power transmission, smoother for motors, and provides constant power flow. Topic 25. Explain the relationship between and perform calculations involving frequency, number of pairs of poles, and speed. The speed of a generator, the number of pole pairs it has, and the frequency it produces are all linked by one main formula. The frequency equals the rotational speed multiplied by the number of pole pairs, divided by 60. In this formula, the frequency is in hertz, the speed is in revolutions per minute, and the number of poles is counted in pairs. If we rearrange the formula to find speed instead, it becomes speed equals the frequency multiplied by 60, divided by the number of pole pairs. There are 2 key ideas to remember. If there are more pole pairs, the alternator needs to run slower to produce the same frequency. If there are fewer pole pairs, it must run faster. For example, on a 50 Hz system. A 2-pole, or 1-pair, alternator must run at 3000 RPM. A 4-pole, or 2-pair, alternator must run at 1500 RPM. And a 6-pole, or 3-pair, alternator must run at 1000 RPM. This relationship is very important when matching alternators to prime movers, because the running speed must suit both the mechanical drive and the electrical frequency required, bringing it all together. Once all the pieces are put together, alternators make perfect sense. Their construction determines how they generate power. The rotor type must match the speed in the prime mover. 3-phase windings turn the motion into stable, balanced AC power. And the pole-speed frequency relationship ties everything together, because an alternator must spin at the correct speed to produce the correct frequency. Understanding these ideas gives a complete picture of how alternators and power stations and generators operate. Summary: alternators convert mechanical to electrical energy. Construction types include rotating armature, rotating field, and polyphase. 2 rotor types: salient, slow speed, and cylindrical, high speed. Prime movers include hydro, wind, diesel, steam, gas, and geothermal. 3-phase generation uses 3 coils spaced 120 degrees apart. Frequency, pole pairs, and rotational speed are all connected by one simple relationship. The formula says that the frequency equals the speed of the rotor multiplied by the number of pole pairs, then divided by 60. This tells us how mechanical speed is converted into electrical frequency. Fewer pole pairs higher speed, more pole pairs lower speed. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we're learning Topic 26, Prescribed Electrical Work Requiring Inspection. This topic explains which electrical work must be inspected by a registered electrical inspector before it can be connected to supply. This is not optional, it is required by law under the Electricity Safety Regulations 2010. We'll look at what work needs inspection, what Regulation 70 requires, and what Regulation 72 says about companion standards. Let's go through each part clearly. Topic 26a. Explain that certain installation work requires inspection by a registered electrical inspector prior to connection to the power supply. Some electrical work is considered high risk, meaning the safety of the installation depends heavily on correct wiring, correct main arrangements, correct earthing, and correct protection. Because of this higher risk, the law requires that a registered electrical inspector, not the electrician who did the work, must independently inspect the job before the installation can be connected to supply. Examples of work that must be inspected include mains earthing or bonding work, work on main switchboards that affects the main system, work involving mains where the neutral or earthing arrangements have been altered, installations in medical cardiac locations, installations in hazardous areas. High-risk prescribed electrical work listed in the regulations. The electrician must complete all their tests and issue a certificate of compliance, but the installation cannot be livened until the inspector has completed their inspection and signed the inspection documentation. Topic 26b. Detail the requirements of Regulation 70 and list the installation work that requires inspection. Regulation 70 is the main rule that tells us what work must be inspected before connection to supply. In spoken form, Regulation 70 requires 1. Inspection must be completed before connecting high-risk prescribed electrical work to a power supply. 2. The inspection must be done by a registered electrical inspector, not the person who carried out the installation work. 3. The inspector must confirm that the work is electrically safe. The work complies with the regulations. The work complies with AS/NZS 3000 and any other applicable standards. Work requiring inspection under Regulation 70 includes work on mains that involves the main connection, earth electrode, or earthing system. Work where the main earthing or bonding conductors have been altered or replaced. Work on main switchboards affecting earthing or main links. Installation work in hazardous areas. Medical locations classified as cardiac protected. Any work listed in Schedule 1 that is classed as high-risk prescribed electrical work. The key point: if the safety of the main system, the earthing system, or the supply protection is affected, an inspection is required. Topic 26c explain that Regulation 72 cites companion standards that cover the inspection requirements for installation work in addition to AS/NZS 3000. Regulation 72 tells us that inspection is not based only on AS/NZS 3000. Some types of installations require additional standards, called companion standards, which must also be checked during an inspection. Examples of companion standards include AS/NZS 3012, construction sites; AS/NZS 3003, medical electrical installations; AS/NZS 60079 series, hazardous areas; AS/NZS 3010, generating sets; AS/NZS 3017, electrical testing practices. So when an inspector carries out an inspection, they must check compliance not only with the wiring rules, AS/NZS 3000, but also with any companion standards that apply to that specific installation type. This ensures that specialized installations, such as hazardous areas, cardiac rooms, or construction sites, meet their extra safety requirements. Bringing it all together. Topic 26 explains the electrical work that must legally be inspected before it can be connected to supply. Regulation 70 lists the work that requires inspection, mainly high-risk installation work involving mains, earthing systems, hazardous areas and medical installations. Regulation 72 reminds us that inspections must consider not only AS/NZS 3000 but also any companion standards that apply to the particular type of installation. Understanding Topic 26 is essential for keeping installations safe and working legally under the Electricity Safety Regulations 2010. Summary. Some installation work must be inspected before connection. Only a registered electrical inspector can do this inspection. Regulation 70 lists high-risk prescribed electrical work requiring inspection. Work involving mains, or hazardous areas requires inspection. Regulation 72 requires inspectors to consider companion standards, not just AS/NZS 3000. Installation cannot be connected to supply until the inspection is complete. Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Today we are learning topic 27, lighting. Lighting is a very big part of electrical work. It affects safety, comfort, color visibility, and energy use. As electricians, we must understand lighting terms, lighting levels for different workplaces, how different lamps operate, and common faults, hazards, and applications. We'll work through each subtopic one by one, using clear and simple language. Let's begin. Topic 27a. Define the following terms and state the unit: luminous intensity, luminous flux, illuminance. To understand lighting properly, we need to know these three basic terms. Luminous intensity. This tells us how much light is sent out in a particular direction. The unit is candela, CD. Luminous flux. This is the total amount of light a lamp produces in all directions. The unit is lumen, LM. Illuminance. This tells us how much light actually lands on a surface, like a desk or a workbench. The unit is lux, LX. 1 lux equals 1 lumen per square meter. Topic 27b lists the essential components required to produce good illumination. Good lighting is not just about putting in a lamp. You need a suitable light source for the task. A luminaire, the fitting that directs light where it's needed. Good light distribution, so the space is evenly lit. Acceptable brightness levels, avoiding glare. Suitable color rendering, so colors look natural. Good maintenance, such as clean diffusers and working lamps. Topic 27c. Explain that recommended and recognized minimum levels of illuminance are required for various work areas. Different workplaces need different lighting levels. For example, corridors need lower lux. Offices need medium lux. Workshops, kitchens, and detailed work areas need higher lux. These recommended minimum levels come from lighting standards and are used to make sure workers can see clearly and safely. Topic 27d. Explain the basic principles of operation of the following. Sodium vapor low pressure. Uses sodium metal vapor. Produces yellow light. Very high efficiency. Sodium vapor high pressure still uses sodium vapor but at higher pressure. Produces whiter light than low pressure. Mercury vapor high pressure uses mercury vapor. Produces bluish white light. Metal halide uses mercury vapor plus metal halide salts. Very bright white light for sports grounds and car parks. Neon lighting uses neon gas and glass tubes. Produces colored light for signs. Incandescent heats a filament until it glows. Low efficiency, short life. Fluorescent low-pressure mercury vapor produces UV light inside the tube, and the phosphor coating converts it to visible light. Halogen, a type of incandescent lamp using halogen gas. Brighter and longer life than normal incandescent. Topic 27e. Compare the output efficacy, color output, handling requirements, effects of vibration, ventilation of the above lamp types and practical applications for each type. Incandescent, low efficacy, warm color, sensitive to vibration, used in domestic lighting. Halogen, better efficacy, whiter light, gets very hot, needs good ventilation. Fluorescent, good efficacy, good color rendering, needs a ballast, common in offices. Metal halide, very high output, bright white light, used outdoors. Mercury vapor, medium efficacy, bluish light, older technology. Sodium, LPs/HPS, very high efficacy, poor color for LPs, used for street lighting. Neon, decorative, colored signs, low power. Topic 27f. Explain color rendering and give practical examples of applications. Color rendering describes how well a light source shows the true colors of objects. A high color rendering lamp makes colors look natural. Examples. Retail shops use high color rendering lights. Workshops also need good color accuracy. Street lights, low pressure sodium, have poor color rendering. Topic 27g. Explain the stroboscopic effect of discharge lamps and how this effect can be minimized. Fluorescent and other discharge lamps flicker at twice the mains frequency. This can make rotating machinery look like it is stopped or moving slowly, very dangerous. It can be minimized by using high-frequency electronic ballasts, using multiple lamps fed from different phases, choosing lamp types that do not flicker. Topic 27h. Describe with the aid of a circuit diagram the operation of a single tube switch start type fluorescent fitting. A switch start fluorescent has a tube, a starter, a ballast. When power is applied, the starter closes briefly to heat the electrodes. Then the starter opens, creating a voltage spike from the ballast, striking the arc inside the tube. After that, the tube stays lit. Topic 27.1. Describe the common faults that occur with single-tube fluorescent fittings and explain how these are overcome. Common faults include flickering, usually a faulty starter tube not striking, faulty tube or ballast, blackened tube ends, tube near end of life, intermittent operation, loose connections. Fixing depends on the fault. Replace the starter, replace the tube, or check wiring and ballast. Topic 27j. Describe the hazards that are present with gas discharge lamps and their control circuits. Hazards include high starting voltages, hot lamp surfaces, UV radiation from damaged lamps, risk of lamp rupture, metal halide, ballast overheating if ventilation is poor. Always isolate. allow lamps to cool, and follow safe servicing procedures. Bringing it all together. To bring everything together, Topic 27 teaches us how lighting works, what lighting levels we need for different environments, and how different lamps operate. We also looked at color rendering, faults, stroboscopic effects, and safety hazards. Understanding lighting helps you select the right lamp, install it safely, troubleshoot faults, and comply with workplace lighting standards. Summary. Luminous intensity candela. Luminous flux lumens. Illuminance lux. Good illumination needs correct distribution, color, brightness, and a suitable luminaire. Different work areas need different lux levels. Lamp types: incandescent, halogen, fluorescent, sodium, mercury, metal halide, neon. Color rendering affects how colors appear. Stroboscopic effect must be minimized. Fluorescent switch start uses ballast plus starter. Common faults: tube, starter, ballast, connections. Gas discharge lamps have high voltages, heat, and UV risks.